Good morning, everyone, and welcome to our lockdown studio here at the University of Wolverhampton. I am Dr. Martin Kashara, and I'm here with the fabulous Heather Angel, and we are from the award-winning STEM response team. And welcome today to our Saturday STEM Spectacular. Now, we wouldn't be able to put events on like this without partnering and collaborating with other fantastic associations. And we're really fortunate to have been collaborating with the Association for Science Education to put on this event that's going to happen from 10 till 2 today. So we're very lucky to have a representative from the ASC today. So we've got Francis Evans, who's one of the field officers from the ASC, to say a few words about what the ASC does and the kind of events that they run. Thanks, Francis.
Good morning, everybody. Yes, I'm from the Association for Science Education. The association is very much about supporting teachers and technicians through our events, resources, and we also provide a voice for science education. But we're actually there for anyone who's got an interest in science and STEM education. And it's been great to be able to collaborate with an amazing team at Wolverhampton University. They are actually doing all the logistics today, so it's a big thank you to them. Absolutely brilliant. We've got a number of events coming up. I'd like to mention the event we've got on the 8th of December, which is a festive teach meet, what we call putting the fizz back into Christmas. And we've also got our national conference in January. So please do look at our website and see everything that we've got coming up, and indeed some of the resources and things that you might find interesting. I do hope you have a great day, and it's a great big thank you back to Martin and Heather for doing all the work behind the scenes. So that's, have a good day. Back to you, Martin.
Thanks, Francis. That's fantastic. And I will say, yes, we are running the show here from our lockdown studio, and we are running on Zoom, and we all know what these kind of calls are like. So please bear with us if there are some technical problems, like there are screen shares and things like that that are going slightly awry. We all know what it's like in this new world order where we live, basically plugged into things like Zoom and Microsoft Teams. So let me just talk a little bit about what we're going to see today. So of course, our event will start very shortly, and we start by looking at our primary years, and we're going to join some fantastic science presenters to actually look at some primary level activities. And of course, that's suitable for our younger learners, our teachers, and our carers and parents that are at home. That's going to finish probably about 11 o'clock. And then we're going to go on a fabulous laboratory tour of our literally amazing £25 million science building here at the University of Wolverhampton to meet one of our researchers, who is called Isabella Redetska. And you'll see her laboratory, and the work they are doing there is literally changing the world. Then we're going to meet up with some of our other partners across the UK, and we're going to visit Northern Ireland, and we're going to have a trip to Wales. And then we carry on by looking at some subjects that are more for our older learners. So that's really when the meat of our secondary programme will start. Once that's finished, we're going to go on and have a panel discussion with some researchers here from the University of Wolverhampton and panellists from all over the country. And we'll be looking at subject areas all the way from the environment, all the way to habitats in space before we end. So I hope you have an absolutely fantastic day. And what we're going to do, we're going to start by finding out what happened when Teddy went camping.
Hi, my name's Ruth, and today I'm going to be doing an experiment from the Kenban website called Teddy Goes Camping. It's about the properties of materials, but we're going to use a story so we can talk about it. Normally I do this with a class of students, and it means everyone can have a go and we can talk about the properties of materials along the way. It's really good for the Key Stage 2 topic of materials and their properties, and depending on the children's age we can go into more and more detail. The nice thing about looking at properties of materials is it's really easy to do, and you can just use the things that are around you. So you're not going to see any fancy gadgets or gizmos here, and you can have a bit of a laugh at some of the things I have around my house. Properties of material are really important for what we use them for. So here I've got a yoga mat. You can see it's nice and soft. That's because I don't want to have anything hard to put my hands or my feet on while I'm trying to exercise. Otherwise I'm definitely never going to do it. My jumper is made out of material too, and that's sometimes something that we get wrong, that we think material means fabric, but material in this context means anything that you can touch. So you can have something that's made out of material that's plastic. My jumper is made out of fabric and it's nice and soft and keeps me warm on a cold day like today. But other objects can be made out of different materials to use their different properties. This screw, for example, is made out of metal. You can see that it's shiny, and I can feel that it's hard and it's pretty strong. And that means that when you use it to screw things together, it's not going to break or fall apart. Hope it's not missing from anything important. Anyway, let's go on with the story. Once upon a time, there were 3 teddy bears. Their names were William, Douglas, and little Zoe. The 3 teddy bears were the very best of friends. They liked to do all sorts of different things together. One day they decided, being teddy bears, that they'd go on a camping trip. They found a great place to put up their tent, and after a campfire, a picnic, and a bedtime story, they decided it was time to put up their tents and go to bed. William was the first teddy bear to go to bed. He'd thought very carefully when he was packing his bag about what kind of material he'd want to make his tent out of. He thought, well, it needs to be nice and bendy so it will go over the tent frame. But also, I want to be camouflaged so when I'm in the woods, no one will be able to see me and I'll be able to get a lot of beauty sleep. So William decided to use green paper to make his tent. He climbed into the frame and he pulled over the green paper to protect him from the wind and the night. But what do you think happened that night? Sometimes happens when you go camping. The clouds come overhead and it starts to rain. Uh-oh, what do you think's going to happen to William when it rains on his lovely tent? What do you think the properties of the paper that he's made his tent out of are? Should we find out? It rained and it poured. Oh, it rained so much that night. And in the morning, when William woke up, what do you think happened? Oh no! His tent was all soggy. But even worse, so was William. It had rained all the way through and soaked through his tent, and poor William was soaking wet. He was not a happy teddy bear. The next teddy bear to go to bed that night was Douglas. Now Douglas was the kind of teddy bear who always felt chilly, so he wanted a tent that would be nice and warm. He wanted a tent that would be flexible, so it'd still go over the frame, but he wanted it to be nice and soft, and he wanted it to keep all the warm air in the tent so he didn't get chilly during the night. He decided to make his tent out of fabric. It was nice and flexible, but also nice and soft so he could snuggle up inside, and hopefully it would keep him nice and warm that night. So he climbed inside the tent for the night and got ready to go to sleep. Uh-oh, what do you think happened that night? Can you guess? That's right, it rained and it poured. What do you think happened? How do you think Douglas felt when he woke up in the morning? Should we have a look? Oh no! His lovely soft fabric tent was all wet. But even worse, poor Douglas was all soggy. And the worst thing about being soggy is it makes you very, very chilly as well. Douglas was not a happy teddy bear. The last teddy bear to go to bed that night was little Zoe. Now Zoe was a real thinker, so before she packed her tent for the camping trip, she thought long and hard about what kind of properties she would need her tent to have. And she decided, after looking at the weather forecast, that she would need a tent that wouldn't let water through. Can you think of the name of that property? Something that doesn't let water through. It might be something that you have a coat made out of. What do you sometimes call that? Can anyone guess? That's right, she decided that her tent should be waterproof. So she decided that she was going to make her tent out of plastic. The other good thing about making it out of plastic is it doesn't let any light through, so it wouldn't wake her up in the morning. This is a black plastic, so that means that the tent was opaque. It doesn't let any light through. She climbed into bed for the night and put up her tent. Her tent was nice and flexible, so it went over the frame, and it was nice and shiny. So that night, the clouds rolled in, and it rained, and it poured. Don't know about you, but I can already see the rain running off the sides of the tent. Should we see how Zoe was in the morning? She woke up and she took down her tent. And Zoe was lovely and dry. She'd had a really, really good night's sleep, and she was all ready to have all sorts of fun the next day on their camping trip. For the rest of the camping trip, the three teddy bears slept together in Zoe's plastic tent. They stayed nice and dry every night, even if it rained, and they had a lovely camping trip. After their trip, the teddy bears thought long and hard and decided if they were going to go camping again, they might take a camper van. Now it's your turn to design your very own tent. Think about what kind of properties you want your tent to have and then pick some suitable materials to make it out of. I'm definitely going to make my tent out of plastic so it's nice and waterproof. It will keep me nice and dry on a day like today. I'm also going to put a transparent window in so I can look at the stars before I go to sleep. I hope you enjoyed the video. For the resources to go with this activity and other primary activities, please visit our website www.kenbam.com.
Hello, my name's Linda Atherton and I'm going to be running a session now on Science on a Shoestring. What I'm going to be showing you is how you can use simple equipment to do some really exciting science. And what we're going to look at in this session is flight. Today is all about being a scientist, and what is fantastic about being a scientist is that curiosity of wanting to know answers and wanting to know why things work or how things happen. So it's asking lots of good questions. So what I'm hoping today is when you go away and you try these ideas out yourself, you'll be thinking of all sorts of questions that you could ask. And the other thing is, we as scientists need to be really good lookers and explorers and are looking to see what happens really carefully. If we can do that, we can describe what happens, and then hopefully we can explain why that has happened as well. There are lots of different questions we can ask, and that's really important because of the curiosity. Where is something? What can we do? Can you see here, there's so many different ways that we can ask questions to find out answers. Okay, so what do we need? You'll need different types of paper. That could be newspaper, that could be scrap paper, it could be a paper bag, all sorts of different types of paper. And what I'd like you to do is, when you're collecting those different types of paper, look at the properties of them. Are some floppy than others, or some more rigid? Because that's going to be key when we come to our designs, when you go off and do your own designs. You'll need some scissors, you'll need some straws, and you'll need some sellotape. If you haven't got any straws, you could always roll up a little bit of paper to make a straw-like strip. It's entirely up to you. Okay, we've got the equipment. We're now going to make paper hoops. So what you need to do then is you need to cut out strips of paper about 3 centimetres in width to start with, and when you've got those strips of paper, connect one end of the strip to the other end to make a hoop, and you'll make different hoops of different sizes. And the important thing is to be looking at the properties of those hoops. Are some hoops more rigid than others? Do some hoops keep their shape more? Because that's going to be important when we're thinking about using some of those hoops in our designs that I'm going to show you now. Here you can see a hoopster, and what I've done is I've got 2 hoops and I've connected them together with a straw. Now the important thing is, with a hoopster, if you want to make one of those as your flying machine, is that you have one hoop that is half the size of the other hoop. So the small hoop, for example, at the front could be 12 centimetres, and it's important then that the hoop at the back is twice that, 24 centimetres. When you get more skilled, you might want to change those diameters as well to see if it has any effect. But to start with, we're going to make a simple hoopster with the smaller one being half the size of the bigger one. Now what we can do is, once we've got that simple design as well, we can start changing things. We could make the hoops the same size if we wanted to. We could add wings. That's entirely up to you. But you need to be looking at the paper, and you need to be looking at the properties of the paper and thinking, do I want floppy paper? Do I want rigid paper? What paper have I got? Can I make the same thing with lots of different types of paper? Will that make a difference? Remember, scientists all the time are changing variables and thinking about how those might affect what happens. You can even add more hoops. So here, instead of putting them just at one end, I've got one straw and I've stuck on lots and lots of different hoops of different sizes in different places. I wonder if that's going to make it any better. But you could also play around with the design as well. This is still 2 hoops, but now what I've got is 4 straws connecting the 2 hoops together rather than 1, and those 4 straws are evenly spread across the hoops. The big hoop, the straws are inside, and they're stuck on the outside of the smaller hoop. I wonder if this design is any better. Right, now this is where the fun starts, because now we've got designs. We might just have one design to start with, or we might have lots of different ones, because we now need to test them out and see what happens when we start flying them. If you look at the picture, you'll see I've got a hoopster in my hand. At the front is a small hoop, and at the back is the large hoop, and I'm going to throw it like I would do any normal paper plane. The thrust will be moving it forward. I'll be getting drag from the air, but I'll also be getting lift, and the weight of it will also be affecting it as well. Your hoopster is not your average airplane either. It uses 2 paper hoops instead of wings to create the force of lift that makes it fly. For that reason, it is also called a ring-wing glider. Lift results from air moving more quickly in between the hoops than the air around them. When we throw the hoopster, air rushes into the hoops, creating the force of lift that makes it glide through the air. So, we've got our hoopsters, we've got our other designs. Let's now go and test them out. So here are my models. Let's see what happens when we test them out. The first one to go is the simple hoopster. Notice the small hoop is at the front and the large hoop is at the back. So let's watch what happens. And as you can see, it glided along because of the lift of the air going through the hoops, but it fell to the ground because of the weight and because of drag. But not bad. Let's see what happens with the next one that I did. As you can see with this one, what I've got is I've now put more hoops on. So I've doubled the number of hoops. I wonder if this is going to be better than the first one. Let's see. Wow, yes, it glided a lot further, so seemed to have more lift. Now, the next one, I decided that I would put some blades on it because I was making, as a scientist, a prediction that if I had blades like wings, I'd get more lift, which would mean that it would glide much further. So scientists make predictions on what they already know, and then they test them out and see if they're right or not. So let's see what happens with this one. Oh, that one didn't seem to go as far, and I think probably it was because it was too heavy. So I've got to do lots of modifications on that one. Perhaps I can use different paper or make the wings different. But that's where the fun is as well, by modifying and changing things and adapting them and trying them out. And I've got the final one that I made. And yeah, that didn't go as far. I wonder why that was. But the important thing is, what we're doing is we're testing out all our ideas. We're looking at them, we're perhaps asking questions, and so we're modifying them and making them better. Just to show you, just so you can see them flying again, so you can compare them. It's over to you now. Happy investigating. Remember, be curious, ask those good questions. When you make your models, look really carefully about what happens. Can you describe what happens? And can you explain what happens using some of those words that I've done today, such as lift, drag, thrust, weight? But most importantly, have fun investigating.
Welcome to my kitchen. Today it's all about the volume. No, not that sort of volume. It's about how much stuff we have in a certain space. And we're going to demonstrate this through the medium of candy floss. More specifically, I want to know how much candy floss out of this tiny jar it takes to fill this massive tub. Let's get straight to it. First of all, what is candy floss? Well, as to candy floss is sugar. And the good thing about sugar is that it doesn't really take up much space. That much is more than you need for a day. How does a candy floss machine make candy floss? It works in a very simple way. Underneath here, we have some heating elements. They get very, very hot. And this little disc spins round and round and round. You'll notice that in the top, though, there is a space. And in that space, we can spoon some sugar. There's a little sugar in. Let's switch it on. Now, as that sugar warms up, it starts to melt. And as it melts, it passes and spins out to a little groove that sits on the outside of that spinning disc. Candy floss is starting to appear. As the sugar is melting, it's been spun into very, very thin melted strands. And what that means is that it takes up quite a bit of space. Ooh. It's growing nicely, isn't it? And still it keeps going. This is why candy floss takes up so much space. It's so much bigger, it has more volume, it takes up more space for the same amount of stuff as just the raw ingredients. And the reason being is because what we're actually wrapping up is not just the sugar, but also lots of air. I think that's our lot. So from 1 spoon, we actually managed to make that much candy floss. But did we add anything else to it? No, that was just sugar, wasn't it? In fact, there's still some sugar left inside. So we didn't even use all that much sugar to make that much candy floss. Let me just prove that. I'm going to wait. Is that set to 0? If I pop it on, it goes up to 4 grams. How much does that spoon of sugar weigh? 1 spoon of sugar. Weighs a lot more, 16 grams. However, there is a lot of sugar around the inside of the bowl. So what would I do with that sugar? Would I add it in? Well, let's do that. And how much sugar do we now have with the candy floss and the crunchy bits that were wasted around the outside? We have 16 grams. We haven't gained anything, we haven't lost anything, but what we've got is some very crunched up and melted sugar, and we've got some very fine candy floss sugar, which takes up a lot of space. I don't really want to keep making candy floss all day to fill my tub, so I need to work out how much candy floss 1 spoon makes. If I can do that, I can work out how many of those will take to fill this. We're going to do the maths on this in a minute. Let's first of all work out how much volume of candy floss we get from 1. The volume, we've seen it's about that much, but we can do better than that. Because nobody really eats the crunchy stuff that's left around the outside of the bowl, I'm only going to collect the stuff that comes off that actually is candy floss. The other stuff is sugar. Sugar that if we mash it up and pound it up, we can use again. So at least I'm recycling some of my waste. Now we're getting into a lot of melted sugar. The temperature is just right. I think that's got the last of it. Now this time I'm not going to wait and get the weight of it. I'm actually going to see how much space it takes up in my little measuring jug. As actual candy floss, that's about half a jug. Now I think it comes in around about the 250 mark. That means that I've got, well, 250 millilitres. Now that's strange because I'm talking about volume, I'm not talking about grams, how heavy something is. I'm thinking about how much space it takes up. So how many 250 millilitres will it take to fill this? Quite a few. Let's get onto that with some maths. That's tied it up a little bit. What have we learned? Well, what we've learned is that 1 spoon of sugar weighs 16 grams, and that makes 4 grams of candy floss, which has a volume of 250 millilitres or 250 cubic centimetres. So what do we need to do next? Well, we need to work out what the volume of our tub is. And that's a little bit more complicated. First of all, though, we need to work out what the area of the bottom is. Now, that's a lot easier when we come to work out the area of a square, for instance, or a rectangle, because what we do is we multiply the length by the breadth. For instance, here we have a square which is 1, 2, 3, 4, 5, 6 across, and 1, 2, 3, 4, 5, 6 down. All we do is multiply 6 times 6 equals 36. So that's fine. That's how we work out the area of a square. But did you notice our tub? Yeah, it's not exactly square. In fact, it's mostly round. So we need to do something different now. When you come to measure a circle, you notice that you can't just measure the sides by each other because it doesn't really have one. So we have to use a special technique. So first of all, we're going to measure how far across our circle is. Across it is 34 centimetres. So 34 centimetres is the diameter. That's how far it is all the way across. Now, when you calculate the area of a circle, you need to halve that. I just need to know what the radius is. Now, the radius is the distance between the centre and the edge. Now, the radius is obviously going to be half because it's not all the way across, it's only halfway across. So that is 34 divided by 2, and that equals 17. 17 is our magic number for radius, but that just gives us from the centre to one edge. What we have to do is we have to multiply that by itself. So that is 17 times 17 equals 289. Now keep that number in mind, because what we have to do now is multiply that by this magic number called pi. Not steak and kidney pie, chicken and mushroom pie. This is a special kind of pie, and it just is a number. It's a strange number. So I multiply that by pi. Oh, and it gives us a massive number, 907, and then some more bits. But it doesn't actually mean much to you and I. But when we think about what we've just measured, we've measured in centimetres across from the centre to the edge. So that's centimetres, and it's not just centimetres because that's a measure of length. This is a measure of area. So actually we call it centimetres squared, and we put a little 2 on it just to show what we've done there. But that's just the area. It doesn't give us the volume because we also have height. So what we need to do is multiply that number by the height to give us the volume in cubic centimetres. Actually, it's 40 centimetres. So let's do that. Multiply by 40 equals, ooh, it's a big number. It is 36316.8. Wow, that's big. But what does it mean? Well, that is centimetres cubed. We had centimetres squared for area, centimetres cubed for volume. That still doesn't tell us how many balls of candy floss will fit in it. What did we say that our candy floss had a volume of? It was 250 cubic centimetres. So all we need to do is divide this big number by 250. Gives us 145.2. Now that tells me exactly how many balls of candy floss will fit in my tub. 145 of them. But it still doesn't answer the question as to how much sugar it would take. Go back to the beginning. Remember that each ball actually needed 16 grams of sugar to make. That's 16 grams times 145. And we get 2,324 grams of sugar. That's the same amount of sugar that you would find in 464 jelly babies. I didn't have that many jelly babies. Here, I've got 1/10 of that. That's the amount of sugar times 10, and then we can know how much sugar goes in to fill up our tub of candy floss. So let's have a quick look back at what we've learned. We learned to weigh some sugar. We learned to then use that sugar to make candy floss. We worked out how much candy floss we had afterwards. Then we worked out how much of that candy floss we could fit into our tub. That might seem a lot of work, but these are the kind of calculations that engineers do every day when working out how much stuff they can fit in a tub, or indeed how big a tub they need to be able to get some stuff in. So that's all from me. I'm hoping that you've had a good day and you've learned something a little bit about the maths behind how we engineer the world around you. Thank you very much. My name's been John Wood.
Hello, I'm Chris Hamlet and I work with a group called Discover Materials who want to show how amazing material science is. We have a website that will soon be full of loads of fantastic information for students, parents and teachers to learn more about material science and suggest some experiments you can try at home or in the classroom.
Wouldn't it be great if some things were bigger, such as these sweets? Unfortunately, we do not have a growth ray to make them bigger, but we do have a magnifying glass to make them look bigger. So magnifying glasses can be used to look at the surfaces all around the home, the garden, and to explore the world around you. Lenses bend light and make things look bigger. Today we're going to look at a few different lenses and microscopes that can help you investigate the world around you. So the next one is this. It's a pocket microscope and you can get them for about £10 to £20. This one has got a light on it to make it easier to image, and to get the image you simply place the microscope over what you want to have a look at, and then you look down the lens, which isn't very easy to line up to actually keep it still, so you can see the bits that are getting darker around the image that keep coming and going. They're due to not be able to hold the camera stable enough. As you can see with the pocket microscope that I showed, it can be tricky to get a good photo of what you can see in the microscope because of alignment issues. But you can get these clip-on lenses, which are absolutely fantastic for taking pictures. So they clip just over the lens of your smartphone or tablet, and you can line it up like that. And then we shall have a look at one of these pencil lines again. You can see the pencil lines nice and clearly. And then you just simply take a photo. I took several of these lenses with me on an outreach event to a primary school, and these are some of the images some of the children got from around the playground. Now we're going to look at a USB microscope. So these start about £30 to £40 and they plug directly into your laptop or PC. So the advantages of this kind of microscope is that you can save the images directly to your computer, and they've got fairly bright integrated light. So you could just place this on the object you want to look at, in this case the pencil line on the paper, and you can adjust the brightness and the magnification, and also, as you can see here, bring it into focus. So what we're going to do next is go outside. I'm now outside and I've got my magnifying glass, my clip-on microscope lens. So let's go and see what we can see. Looks pretty cool under the magnifying glass, but now we can put on our clip-on lens and see what it looks like under there. Wow. Look at that. The structure is beautiful. Oh, and then you can see the lovely veins in the leaf behind it. So far, we've looked at these 4 examples of lenses and pocket microscopes that you can get to have at home to look at the world around you. This is an optical microscope. It's a bit more expensive and it's been lent to me by the people at the company Zeiss. So what you do, you get a sample, in this case the pencil writing on the paper, and you slot it in there. You then look through these eyepieces, which are about 10 times magnification, and then you've got different lenses here to magnify, and you can light it from above or below. And with this microscope you can use different kinds of light, so just normal light and also something called polarized light. So what you do, you have to look through the eyepiece, and then we can move the stage up and down to get the sample in focus. So as you can see, we've getting it in focus there. We're in the kitchen, and what we're going to look at under the big optical microscope are some sugar, some salt and some pepper. And then after we've looked at them under the microscope, we're going to add some hot water to them, and then evaporate the hot water off, and then have a look at them again under the microscope. So we'll put some pepper in there, some salt in there, and some sugar in there. Then we just add a little bit of hot water, so to dissolve them, but as you can see the pepper doesn't dissolve, and then we'll just leave them until all the water evaporates off, so leave them in a nice warm place. Now, as you can see, the water's evaporated off, leaving the sugar and the salt behind. So we can see that the sugar has gone from those rectangular crystals to these more snowflake-like crystals, and that the salt has gone from the sort of like powdery granular structure to these beautiful square crystals. So I hope you enjoyed learning about some of the microscopes and lenses that you can buy to have a look at things around the home or in your garden or at school in your playground, and also the introduction to this optical microscope here. So have fun exploring the world around you, and I'm going to leave you with a quick quiz, which is 4 pictures I took with the clip-on lens, and you have to guess what they are. Thank you very much. Okay, so here are 4 images I've taken using my clip-on microscope lens of things that you might find around the house or in the garden. So you've got a minute to guess what they are. Right then, now it's time for the answers. The first one was bread, which was my sandwich. The second one is a duck feather. And you notice there was a feather in my garden. The third one is a jammy dodger, the inside of one of those. And last but not least, that fibrous structure is a tea bag. So I hope you enjoyed that and enjoy the rest of the Saturday Spectacular.
Hello, my name's Ruth. I want to see if you can guess what we're going to be learning about today. So, think carefully, what do these things have in common? Remote control, my exceptionally snazzy head torch, my MP3 or music player, and a laptop. Other brands are available. So I'm hoping right now that everyone's shouting this word at me. That's right, they all contain batteries. So some of these are actually quite different batteries from each other. For example, this head torch takes really simple AAA batteries that I use up and then I throw away. But the laptop, what do you do with this or with a mobile phone when it runs out? You plug it in, right? And it recharges, and sometimes the battery gets worse and worse, and after a long time you have to buy a new battery or a whole new laptop. So this is what we're going to be learning about today. There are lots of scientists working on designing new batteries. So the really cool thing about batteries is you can refill them with new electrical energy using renewable sources, so like solar power or wind power or anything like this. So it doesn't have to be burning fossil fuels. Rechargeable batteries are called lithium-ion batteries, and we use them in all sorts of things, and we're going to be using them a lot more in the future. So you might have heard about battery-powered cars. They use lithium-ion batteries too, and that means you can plug your car in at night and your battery will recharge and you'll be able to drive your car all around the next day. There's a lot of science that actually goes into designing a battery. For example, when you've finished using a battery, so if you've had a laptop for a long time or your phone for a long time and the battery's not working very well, it's really important that we recycle them, just like we'd recycle things like paper and plastic all the time now. But a battery is a lot more complicated than a piece of paper. It's got a lot more ingredients in it, and we need to be able to separate them all out so we can reuse them again. So if you imagine we cut open this battery, there's going to be all sorts of different things inside, and we need to be able to make sure that we separate them safely. So today we're going to do an experiment about this. So this fits in with the key stage 2 topic of separating materials. But we're also talking about what real life scientists are doing in universities, like the University of Birmingham, to separate the different parts of a battery so we can recycle them in the future. But we're going to use something much more exciting. We're going to use the humble Crunchie. So, if we take a look at a Crunchie, we can see that it's made of different delicious components. It's got the nice bit of chocolate around the outside, and inside it's got that lovely honeycomb centre. So how do you think we're going to separate these two different types of material so we can recycle our Crunchie? So recycle means we can take it all apart and put together a whole new Crunchie. I'm going to show you 3 different methods for separating the different parts of the Crunchie, and then we're going to think about what the positives and negatives of each different type of method are. Think about if they could be used for batteries, and if it would work if we had a big factory full of lots and lots of Crunchies. Let's get started. The first method for separating our Crunchie bar is called pyrolysis. Can you say that? Pyrolysis. It sounds really, really complicated, but if you like X-Men like me, you might know there's a character called Pyro who makes fire. That means we like heating it up. So what we're going to do, we're going to bash up our Crunchie bar and heat it up in the microwave and see what happens. This is the fun bit. We can take our rolling pin and bash up the crunchy bar into lots of little pieces. Now we can pour out the parts into a microwavable bowl. In the battery industry, they call this shredding, and they literally take a load of batteries and put them through big shredders so they're broken up into little pieces like this. Let's see how it goes in the microwave. So now you can get an adult to help you and put your pieces of crunchy in the microwave for about 20 seconds. In the classroom, you could probably do this with just a bowl of warm water. When you take it out, you might be able to see the chocolate's gone all soft, and you can see the lumps of the cinder toffee from the middle. This means you could use something like a sieve maybe to separate it out. As you can see, it is all clumpy and it doesn't look very nice, although I still might be tempted to eat it. Believe it or not, this is actually one of the most popular ways that we currently recycle our batteries. As you can imagine, it does not work very well. The second method we're going to use to separate the parts of our crunchy bar battery is called solvation. This just means that we're going to add a liquid, in this case water, and see if we can use that to separate out the different parts in our battery. First, we need to shred it. This time you can put the parts of your crunchy bar into a glass, or if you prefer, a plastic bowl or beaker. Here you can see it's already broken into small pieces, so that way when we add the liquid, we hope some parts will start to dissolve and other parts won't. Then give it a quick stir. So you can already see some parts of the crunchy have dissolved into the liquid. You can tell this because the liquid's got a brown orange colour, but also you can see that there's some solid chocolate at the bottom and actually a little bit of the honeycomb still floating in the top. What you could do now is pour that through a sieve to separate the different parts of your battery, and then you could even talk about the different ways you could remove the water so you can get the sugary centre back out. So this is the solvation method. We do something similar to this with batteries, but we wouldn't use water as the solvent. We might use a stronger chemical. So already we've got two methods that we can compare. This is the residue left from my pyrolysis, and this is from the solvation. Maybe you can already start to think about which one you think is better and which one you think would work with lots and lots of crunchy bars. Now we're going to do the final method for separating out our crunchy bars. The idea of this one is very simple. It's manual separation. So take a knife that's not too sharp and try to manually remove the chocolate from the outside. The aim is to remove some of the chocolate without cutting off any of the honeycomb. As you can see, this method takes a lot longer, and actually I've only done about half a crunchy bar in a minute. I've also made a few mistakes, and there are bits of honeycomb that have come off. If we were thinking about doing this with hundreds of crunchy bars, I definitely wouldn't be volunteering to do it. But if we were doing this with batteries, it would be even more complicated. You'd need an expert who knew how to take apart the parts separately and safely. So it'd be very expensive, and we'd have to pay them a lot of money to work such long hours on such a repetitive task. It would also be difficult to keep it safe with all the workers taking apart the batteries. However, there are some advantages. Generally, the parts have been separated a lot more accurately than with our other methods here. Have a think about it with your class and maybe discuss it. Which method do you think is the best? Thank you for watching my video. I hope you enjoyed it. If you want to look up any more information about this experiment, we have a Key Stage 3 version as well. Please go to the website www.kembam.com.
Well, everyone, we really hope you enjoyed that. And if you're at home today, if you're a teacher, a parent, a carer, a home educator, whoever you are, I hope that you're inspired to be trying some of that fabulous science, technology, engineering, even maths at home or in your classroom, especially now we know we can do separation techniques with crunchy bars and that maths is also candy floss. Now, what we're going to do is we're going to move on in our programme in a second. What I will say is thank you for all of the fabulous comments we've got coming through on the chat. Please keep all that feedback coming. It's really nice to hear that everybody is enjoying what we're putting out today. We're also on YouTube Live, of course. So do comment on there. You can watch on there too. So if you know anybody who hasn't got the Zoom link today, they can also watch on our YouTube Live. So if you have got a question, please use the Q&A function because if you do raise your hand, and some people have been doing that, that's fine. But because we've got quite a packed programme today, we can't stop and chat to you sort of verbally like this. So if you ask your question in the Q&A function, everybody gets to see the answer then. So what we're going to do is now we're going to move on. And what I'm going to do is take you on a tour of our fabulous science building, which is called the Rosalind Franklin Building. And it actually represents a £25 million investment in science practical teaching that the University of Wolverhampton has made. And actually, it is an example of science teaching facilities that people come and see from all over the place. So let's go and see the Rosalind Franklin Building and go and meet one of our fabulous professors. And this is the University of Wolverhampton. And we are standing in the fantastic Rosalind Franklin Science Building. You are about to witness the £25 million investment in science teaching the university has made. And we're here today to actually meet a very special scientist. But that scientist is all the way up on the very 5th floor of this building. So what I thought we'd do at least is just have a little tour around the building on our way up there before we meet the fantastic Professor Isabella Wiedecka. And here we are on the very first floor of the Rosalind Franklin Building. The Rosalind Franklin Building is actually divided into subject areas depending on what sort of floor you're on. So here we are on floor 1. Now, on the first floor, what we have is chemistry. So behind me, you can see that this laboratory is set up for a practical session, ready to run face to face, even in spite of our COVID pandemic, about a subject in chemistry. And what we're going to do is go up to the next floor, where actually we'll see where some of the more biological practicals actually happen. Now here we are on the second floor of the Rosalind Franklin Building. Now if you remember what it looked like before, on the first floor, which was primarily involved in things like chemistry, actually now on the second floor, we're involved more in biological sciences. And here on the second floor, we do things like biomedical science, hematology, anything really, microbiology, anything to do with the things that infect a person or the fluids of of a person. We teach people how to analyse those sorts of samples to be able to actually diagnose disease in real patients. And you can actually see behind me that the laboratory is set up in lots of different ways. You can see we've got microscopes behind us and so on. And also you might see that some of the desks have got tablet devices on a sort of arm. And actually, our students, we can actually get 90 students in here at a time when we're not in a lockdown, of course. So students get a tablet between two, and that allows them to record their data in real time without paper straight into their sort of student learning environment, which is absolutely fantastic. So we have people from all over Europe come and actually see the sorts of things that we're doing here in the Rosalind Franklin Building, because it is considered best practice for science education. But this isn't all, because we're just on the second floor and we've got 3 floors left to go. So here we are on the 3rd floor of the Rosalind Franklin Building now. Now, the 1st floor, as I said, was to do with things like chemistry. The 2nd floor was to do with the biological sciences that concerned the fluids of the body and the infectious things of the human body itself. But this floor is about biochemistry and molecular biology, about DNA and about analysis of fluids that allow us to diagnose disease. And I'm talking quietly because over here we can't show you that at the moment. Right now there's actually a class happening face to face. Even though we are under COVID regulations, we can still have our face to face practicals in a COVID safe manner in these laboratories. And these students are experiencing how to actually use scientific equipment that is going to be their tools of life as scientists as they move forwards through their career. What we're going to do, we're going to move up to the other floors, and they are very special places indeed, because they concern the research that the university does through the Faculty of Science and Engineering. Okay, so let's go and have a look at the 4th floor. See you later, everyone. Bye. Now here we are on the 4th floor of the Rosalind Franklin Building, and this is the absolute hive of the research effort in the Faculty of Science and Engineering. Here there are many different subject areas represented, and there are postgraduate students carrying out their PhD sort of research programs, and also academic researchers here working on loads of different kinds of projects. One of the things we do particularly in this facility here is look at new and improved ways to treat cancer. And that's everything from bowel cancer to brain cancer. And every day new discoveries are being made just in this room. I mean, how fantastic is that? But the scientist that we're going to see doesn't live here. She's one more floor upwards. So let's go and see if Professor Radecka is available on the 5th floor. Here we are on the very 5th floor of the Rosalind Franklin Building. This is the top research floor of the building itself. And here we've got some fantastic facilities. On one side, we've got greenhouses that look out towards the sky, and they're lit all the time. So if you look across Wolverhampton at night time, you can see a sort of pinky purple glow from the top of this building. And this is our greenhouses being lit 24 hours a day to grow the experimental crops that they're looking at here at the University of Wolverhampton. But behind me is the home of one of our fantastic research groups, and that's the biopolymers research group. And the lead of that is Professor Isabella Radecka. So let's go and meet her now. Yeah.
Hello, I'm Professor Isabella Radecka, and this is my colleague,
Dr. Brian Johnston.
And we are in our fermentation lab in the Rosalind Franklin Building at the University of Wolverhampton. And this lab, it's a fermentation lab. As you can see behind us, we have a lot of fermentation vessels, and this allows us to carry on our research in an area of biodegradable polymers. So we use microorganisms, and we grow them most of the time using waste material, and we produce biodegradable polymers. Well, we are in the fermentation lab, so fermentation biotechnology lab. As you can see, we have fermentation vessels here. Those vessels are used to grow microorganisms. They're like little houses for them, and we can really provide them with very good environment, temperature, pH, lots of food, and we can grow them in very good quantity, and we can produce very interesting, valuable products.
Okay, so this laboratory's got lots of different uses. We can analyse different types of plastics here because we work on degrading plastics and making biodegradable plastics to replace those degraded plastics. So in the fermenter, we can grow bacteria that help to break down plastic, and then we can make biodegradable plastic. And this machine here helps us to control the conditions of the reactor, so we can control the temperature with this little belt here. So this can heat up and warm up the vessel. We can also change the pH, and we can also increase the speed of the impellers, which spin around and make the bubbles, so that the oxygen levels can go up and makes the bacteria grow more. So before we start the fermenter, we have to autoclave it in this machine. So we fill up the vessel with water, place it in the autoclave, and it gets heated up to 121 degrees for up to about half an hour, and that kills any bacteria to make sure it's completely sterile. And then we can load whatever we need to load into it, and it can grow without getting contaminated.
Okay, so what we have here is an incubator shaker. So if we want to inoculate or put bacteria into our fermentation vessels, which you've seen before, first we have to make them happy and alive and make enough what we call the starter culture. So we prepare little flasks with a particular growth medium. We put microbes in, and we just keep it here overnight until the microbes will grow. We check if they're healthy, if they are not contaminated, and then this goes to a fermenter for the fermentation process. And as Brian said, for our bioplastics most of the time in this lab, because we produce biomaterials, bioplastics. Okay, as we mentioned before, in this laboratory we work with biomaterials. So we grow the microbes first in a shaker, as you've seen before, then in a fermenter, and then after that we isolate the polymer. And when we isolate the polymer, you can see that some of them, they really like little plastic materials. They behave very similar to plastic materials, but it's fully biodegradable material made by bacteria. And for some of our research, we just use a dirty cooking oil, very dirty cooking oil, which is much different to a fresh oil. And when we use this dirty cooking oil as a food for microbes, they can just produce the bioplastic, the biomaterial. Now, we need to know how good the plastic is. So one of the methods of trying to find out if this plastic is of good quality, we use this machine here, which is called gel formation chromatography. The biopolymers are made from chains. So polymer is a big chain. And now, depending how long is the chain, that reflects on the quality of our plastic. So we have to measure the length of the chain. So we use this machine, which is called gel formation chromatography, to assess this, what we call a molecular weight, the length of the chains in the biomaterials. So Brian, you can say now.
Yeah. Okay. So to prepare those samples, we take a small amount and we melt it down in chlorophyll, and then it gets loaded into the machine through the cassette deck here. So the sample goes in there, then a tiny syringe goes into the sample, sucks up a sample, and then it passes through this column here. And depending on how long it takes going through the column, we can work out its molecular mass. So on the computer will do a graph, and it calculates the molecular mass of those samples. So this is our 3D printer, so we can use our biodegradable polymers, mix it with PLA, polylactic acid, and we can make 3D printer ribbons like this and create shapes like this, or even shapes like human ears. And we've actually been able to, we had a paper a few years ago where we grew human cells on these graphs as well. So it's able to be used for lots of different applications, and the fermenter can also be used to make conditions for human tissue growth on these platforms as well.
Wow, wasn't that absolutely amazing? The work they are doing in this room is literally saving the planet. It's not only replacing plastics that we can't degrade with plastics we can degrade, made from waste that we throw away every day. It's also helping to build the scaffolds that in the future we'll be able to actually grow human organs on. And I think that is absolutely fantastic. I hope you've enjoyed having a little tour around the Rosalind Franklin Building today and meeting one of our fantastic researchers. So hopefully we'll see you again soon. Bye bye. Wow, I'm sure everybody out there watching will absolutely agree. The work that is going on in the Rosalind Franklin Building, in the Biopolymers Research Group, that Professor Radetska heads up, is absolutely mind-blowing. They are taking waste that we all throw away, as I said, every day, and they are using some of the smallest things in nature, a bacteria, to actually change that into something useful, but that is also biodegradable. They are actually combating the problems of plastic pollution. And that's the kind of research that's going on in the Rosalind Franklin Building. That's just a small portion of what we do here at the University of Wolverhampton. Okay, so again, please keep asking us your questions in the Q&A, and keep the comments coming in on the chat. Just remember that anything you put in the chat and in the Q&A is visible to everybody, so it is completely public. Okay, so what we're going to do now, we're going to have a bit of a departure from the University of Wolverhampton, and we're going to go across the UK and meet some of our partners in Wales at TechniQuest and in Northern Ireland at Sentinus. So I hope you enjoy the videos that they've sent us today.
Hi, the show you're about to see has been developed by TechniQuest. TechniQuest is a science and discovery centre based here in Cardiff Bay, so if you're ever in Cardiff, please do come visit. Like all science centres, we are passionate about communicating science in a fun and highly interactive way. We want to engage you with science and get you wanting to know more. We hope you enjoy our show. We all have a body, but how much do you know about it?
Our bodies are more than just a bag of bones. We are huge, complicated machines with moving parts that work together to make sure we stay alive. Think about what parts of our bodies we use on a daily basis. What part of your body do you use to eat chocolate cake? Outside of our bodies to do everyday tasks. On the inside of our bodies, there are many different systems which are helping us to stay alive. There's a word that we use for a part of the body which has a specific job. This anagram here is going to help you find it. See if you can figure out what that word is. organs are parts of the body with a specific function. And as you can imagine, the body has got bones. Now we're going to start today by talking about bones. Every single one of which is an organ. This is Monty. Monty is an adult skeleton. He is made up of 206 bones. However, if he was a little younger, say if he was a child skeleton, or even a baby skeleton, he'd be made up of more bones. You see, when you're born, you start with 170 bones. And over time, these bones will fuse together to form larger bones. Fun fact, babies are actually born with bones by the time you reach your teens. Each Monty bones has a specific function. Some of them are some of them But what is the skeleton actually for? It gives us structure so that we have a shape. Without our bones, we'd just be big sacks of skin. The skeleton allows us to promote the health of our muscles and tendons, and our bones are able to get us moving. Finally, our skeleton protects our organs. The brain is protected by the skull, while the heart and lungs are protected by the rib cage. Without our organs, we would be unable to survive. Now, it's quite difficult to say which one's the most important, but the first one that comes to mind is the brain. Now, I've got a little game of true or false for you. Statement number one, the brain is split into two halves. True or false? This one is true, and to prove it, I'm going to introduce you to my friend. His name is Bob. Now, I'm literally going to look inside of Bob's head now, but he doesn't mind, it's fine, because Bob's made out of plastic. So here I go, take off his head, and we're going to take a look at the brain. Now you can see that you have a left and a right side to your brain. The right side of the brain controls the muscles in the left side of the body, and the left side of the brain controls the muscles in the right side of the body. So if you wave your right hand at me, it's the left side of your brain that's at work. Statement number two, the brain is the size of your fist. Is this true or false? As you can see, the brain is about the size of two fists put together, so this one is false. You can try this for yourself. All you need to do is take your two fists and hold them up here. Statement number three, there are only 5 senses. Is this true or false? This one is false. There are 5 main senses, that of hearing, of sight, of smell, of taste, and touch. But there are actually several others. Hunger and thirst are senses, balance is a sense, pain is a sense as well, and there's also another sense which tells your body the position and movement of your limbs and muscles without actually looking at them. And we can try this for ourselves. All you need to do is close your eyes and take your index finger and raise it up to your nose. Now open your eyes. You've been able to touch your nose without smelling it, without tasting it, without hearing it even. You've been able to do this because of a sense called proprioception. Proprioception is the same sense that you use to climb up the stairs without looking at your feet. It's pretty cool. Now the brain might be the organ which tells pretty much everything in the body what to do, but the hardest working organ would have to be the heart. The heart is a muscle. And just like any other muscle in your body, it contracts and relaxes continuously. The difference with the heart, though, is that it never, ever gets tired. Let me prove it to you. I have a challenge for you. Hold up your fist and start pumping it, just like this. That's it, just keep pumping. Now, do you think that you could keep pumping your fist for the next hour? For the next day? For the next week? For the next month? For the next year? For the rest of your life? No, because I'm already getting tired. Can't do it. It's too difficult. But the heart can. 118,000 times a day for the rest of your life, your heart will pump continuously. Our hearts pump blood around our body, and the blood carries oxygen, which our organs need to function. But it doesn't beat at the same speed all the time. It can change its speed depending on what we're doing. The speed at which our heart beats is what we call our heart rate, and it's measured in beats per minute. Let's see how our heart rate can change depending on what's going on. I am currently watching TV and stuffing my face with popcorn. My body isn't working very hard. If you listen, you can hear my resting heart rate. It should be about 80 beats per minute. Alright, I think I've been here long enough, and it's time to do some exercise. Let's begin with a light jog. As I move, my muscles are using up more oxygen from the blood, so my heart needs to pump faster to supply more oxygen. I don't think I've done enough yet, so I'm going to keep going for a little while. My heart rate is starting to increase a lot. I'm breathing heavier and more oxygen is being delivered around my body to catch up. Just then, we were listening to the heart beating, but have you ever wondered what actually makes that noise? To explain, I am going to have a race with myself to see which one of me can pump up these balloons the quickest. 3, 2, 1, and go! Well, me, you haven't done very well, have you? The truth is, this wasn't a fair contest. Let's look at the difference between these two pumps. One of the pumps has this hose attached. Its proper name is a valve. Inside a valve is a little trapdoor which allows air to move through it in one direction, but is forced shut when the air tries to go back the other way. When we pumped our balloon with the valve, the air didn't escape the balloon because it couldn't. Sorry, me. This is similar to what happens inside of our hearts. There are valves which open and close and force the blood to go around in the same direction every single time. When the valves snap shut, that is what makes the sound of the beating heart.
Okay, good morning everyone. My name is Gerard Hughes. I'm on Saturday STEM Spectacular here from Northern Ireland. You're all very welcome, mums, dads, guardians and young people of course, because young people are our next generation of scientists and engineers. I want to do a couple of activities with you, very short activities, stuff that you'll have around the house. And the first short activity is the first motor. Okay, it's called the homopolar motor. It was designed by Michael Faraday 200 years ago next year in 1821. So it's been around a long time. Now, as a motor, as a working motor, it's not particularly efficient. It's not particularly strong. And of course, it's been superseded by the coiled motors. But we'll not talk about those today. But we'll actually have a look at the homopolar motor and how it works. The other activity I'd like to do with you is the Cartesian diver. Again, it was a toy that was developed and designed and developed by René Descartes, French philosopher, mathematician and scientist. In fact, in the past, many of the philosophers and scientists actually were in fact also dabbling in science as well. And in fact, many of these guys were self-taught. So there's an interesting lesson in that you can actually teach yourself a lot of science if you're interested in it. So let's get the practicality started and we'll build some of these. Now for the homopolar motor we need a pair of scissors, we have a paper clip. Now I have the paper clip is sitting on a piece of fluorescent paper and that's where we'll be able to see it rotate later. Strip of fluorescent paper. I tried to do that on, it didn't glue particularly well. 1 AA battery, that's all you need. You need a wood screw. You'll have those around the house. Most of these things you have around. The only thing you'll need to have are the neodymium magnets. They're very, very strong. They're literally it does take a lot of effort to get them separated. So I'm going to use 2 of those. They're quite cheap. They're about 70 or 80 pence each. You'll get them on Amazon. A length of copper wire, okay, and a glue stick. The glue stick I was for sticking the fluorescent paper, didn't work, so we can bin those. Okay, but I'm sure you have glue sticks around the house. So what we'll do is we'll get started. First thing, you get the wood screw. You have no problem. These literally will, it has to be obviously a steel wood screw, but they really are. I mean, you will not shake that off. And the next thing I want to do is I'm going to put the paper clip on, and I want to try and put it centrally on a piece of fluorescent paper and stick it. Okay, there. Okay, simple as that. I want to make sure that the wood screw is central on the magnet, because we want it to be even in its rotation. That'll stick on there easily enough. You notice it's actually starting to move already, but now and then I'll explain to you shortly. So I keep my index finger on the one end of the wire. Now both ends of the copper wire have to be stripped. I'm using insulated wire here, and as soon as literally, okay, and the secret of making this work, and as you can see it'll rotate at about 2000 RPM, but the secret of that is to bring the wire in literally horizontally. When you bring the wire in horizontally, it means the direction of the current is going in that direction. The magnetic field will be acting in perpendicular to that, up in this direction. And of course what you use is of course what they call the right hand rule, if I can get this right. The right hand rule, you've got your current going in that direction, you've got your magnetic field going in that direction, and the third force is called the Lorentz force. It will go in that direction, but it can't actually go in that direction, so it actually causes the whole paper clip to rotate. Okay, so that's basically it. Again, designed by Michael Faraday 200 years ago in 1821, and it's actually unbelievable that Michael Faraday could do with that with the very, very crude materials that he had at the time. That's 200 years ago. So great credit. Michael Faraday is also known as the father of electricity. Now that term was also used for people like Tesla and Nikola Tesla, and also Thomas Edison. And as you know, Nikola Tesla, he was one of the forerunners of what they call the alternating current. Now this type of current we use here is direct current, because coming from the battery, it's going from literally going from one end of the battery right round to the other. So it's direct current. It doesn't change. The current does not change direction there at all. Whereas in modern electricity, if you plug into a device in the wall, that's what they call alternating current. Literally, the current is changing direction, and it's changing direction. In the UK and Europe, it changes 50 times a second. They call that 50 hertz, and in America, it changes at 60 times a second, when they call that 60 hertz. Okay, so I think we've really covered all of this. But the principle on which it works, and I'll just show you here on this little sheet, maybe that gives it first, is you have the direction of the current is that direction, the magnetic field is coming in that direction, so the resultant force causes the whole thing to turn. And the reason why, as I say, I put the fluorescent paper is so that you can see the rotation. Okay, so our second activity here, we're going to build or put together a Cartesian diver. Again, it was a toy that was designed by the French philosopher and mathematician and scientist René Descartes. It's very, very simple device. It's really all about density, and I'll talk to you about that in a minute or two. So let's start building. So what do you need? You need the plastic dish. Here we have it here, and that's just really to mop up, because I'm sure your mum and dad won't want to mess around the table. We have a large drinking straw. I've put a black one, I've got white ones, different colours here. Pair of scissors, no problem for cutting. Small piece of plastic, too much here, but we'll use a bit of it. Full glass of water. It's important that this is full, actually, because it makes life easier for you. A 2 litre bottle full. It has to be full to the very, very top. Okay? And I mean literally to the top. Okay? In fact, if it's not full to the top, you should literally top it up a little bit. Okay, so I'll put that, so there it is, topped up. Now there will be a bit of displacement when I put the diver in, so just tighten that. Okay, so first thing, sorry, we're 2 layer bottle one, and we have a paper clip, the old paper clip here again. So again, the paper clip, just if you widen out the paper clip, you might have a bit of manipulation to do here. Okay, and you can leave it like that, make it wide on both sides so it's like this. Okay, paper clip, and we can cut our straw in two, so we don't need the bendy bit. Okay, if you've got a straw with a bendy bit on it, that. Okay, then I need to get the middle of it. I want to bend it in the middle, so I need, there we are, there we got it, and we need to shove the straw or the paper clip into it. So there we have it. Now we need to make sure we don't block these ends here. That's very, very important. So we now play about with it, and we need to put some plasticine on it. So we're going to plasticine because we want it just to float in the glass. Now that's, we want the thing. Now this is one that I literally made earlier. This is one, and you can see it, it's just sitting at the top there, just sitting at the top. Okay, we don't want it any more than that. And the last bit is to put this in there. We're going to get displacement when we put this in, as you can see the water coming out the top. Okay, we're going to get some displacement. Now please don't squeeze it while you're tightening the top. Hold it at the neck and tighten the top. Okay, and then literally I'll take some tissue paper over here so we're not making a mess. So literally now, when I apply a little pressure on the bottle, our Cartesian, and then when I release the pressure, the Cartesian diver goes by. Now you get a better effect, of course, if you use black. If you use black straw as opposed to white, you can see it inside the bottle much easier. The thing, of course, is that you have to be careful is do not block the openings of the straw, because what effectively, and if you watch as you press that, if you watch it, you'll notice the water goes up inside. Okay, so do you remember, well, you would know that, or you may have know this already, that whether or not something floats or sinks will depends on the density. The magic number is 1. So anything with a density of greater than 1 will sink, less than 1 will float. Now, density is the weight of something divided by the volume. The weight is the amount of stuff that's packed into it. The volume is the actual space it takes up. Okay, so if you make the number in the bottom bigger than the number in the top, you will get that thing to float. Okay, now what we're doing here is, when I, with the glass here, by altering the amount of plasticine, I was able to get it to a point where the density was 1. But then when I squeeze the bottle, water moves up inside the straw, and of course the weight, the number on the top, becomes bigger, and once it becomes bigger than the number on the bottom, it will sink. So as I say, when I press that, and then of course when I release the pressure, the water comes back out again out of the straw, and it'll come back up. Its density becomes less than 1. Okay, 1 or less than 1, when you just get it to float on the top of the thing. So those are two very simple experiments you can do at home. Literally straws, scissors. The other one with the homopolar motor, the other one, there's all kinds of things you can investigate with it. For example, with the homopolar motor, you could look at what happens if I reverse the magnets around the other way. What happens if I reverse the battery the other way around? Does that affect the direction in which it rotates? That's something you need to find out for yourself. Okay, so thank you. I hope you enjoyed those two fairly basic activities, but they're good fun. Okay, thank you very much indeed, and bye from Northern Ireland.
Let's now talk about the organs which provide the body with a supply of oxygen. Let's talk about the lungs. Place your hands on your chest. Breathe in and breathe out. What are the lungs actually doing? They are filling up with air, which means that the oxygen in the air can be absorbed into the blood. At the same time, carbon dioxide, which has been produced by the body, needs to be gotten rid of. So after you've breathed that oxygen in, carbon dioxide gets breathed out and back into the air. But just how much air do we have inside of our lungs? To find out, I am going to do a little experiment. In front of me, you can see that we have a jug of water which has been turned upside down. What I'm going to do is to blow air from my lungs into the pipe attached. We'll be able to see just how many litres of air I can keep inside my lungs. So far we've looked at lots of big parts of our bodies, but the small parts that you can look at up close are also really interesting. And for that, we're going to use this optical microscope. The first stop is my fingerprints, which are created by small pressures that our developing fingers experience in the womb. Even though there are similar types of fingerprints, such as loops and arches that you may be able to see here, their pattern is completely unique to you. This is why forensic scientists use fingerprints to help identify criminals from a crime scene. Here are my fingernails. These are made from keratin, which is the same stuff that you find in the hairs on your arms and on your head. If you counted all the hairs on your body and asked a chimpanzee to do the same, you'd find that we are just as hairy as they are. The only difference, of course, is that our bodies have hairs which are a lot shorter, and we use clothes to keep our bodies warm instead of a thick coat of fur. My cheeks look interesting, don't they? Can you see the pores in the skin? That's where sweat comes from. But they can also get blocked, which causes spots. Our skin is the largest organ of our bodies and provides a waterproof layer to prevent our inner organs getting swamped with water when it rains or when we go swimming. Both our nose and ears have little hairs in them. In the nose, they filter the air that we breathe, and in the ear, the hairs work with our earwax to prevent bacteria and debris and dust from getting into the inner ear and causing damage. Although we can't see it with this microscope, the inner ear actually contains the 3 smallest bones in our bodies, which are small enough to fit on a fingernail together. Can you see the tiny blood vessels in my eyes? They're called capillaries and prove that absolutely all parts of our bodies need blood and oxygen. What about teeth? They are covered in a thin protective layer of enamel, which is the hardest thing in the body. Enamel protects the teeth when we bite and chew things, as well as making sure we don't feel pain from hot and cold foods. If we damage our enamel, it will never repair itself, so we have to make sure we clean our teeth twice a day and go to the dentist regularly. So far we've looked at our specific organs in isolation, working by themselves, but in reality organs work together in what we call systems. For instance, the heart and the lungs work together in what is called the respiratory system. You can think of it like this: the lungs are like 2 big train stations. The oxygen in the air as you breathe it in are like the passengers that are trying to get somewhere. They are trying to get around the body. And the blood is the train. The oxygen hop onto the train, the blood, and the blood is pumped all around the body to every specific part of the body that needs oxygen. Next, we're going to explore the twists and turns of the organs that help us get the most out of our food, the digestive system. Digestion is the process that your body uses to get the good stuff out of your food, and it begins with the mouth. Here I am getting ready to eat a delicious snack. As you can see, I'm eating some chocolate spread, a banana, applesauce, and chocolate rolls in a sandwich. But what is happening inside my dry though, and that's where the saliva comes in. Saliva is a liquid which breaks down the food and keeps it nice and moist, so it's easy to swallow. The next thing that I need to do is to get the mashed up food from my mouth to my stomach. Luckily, there is a handy tube called the esophagus that connects the mouth to the stomach. Food doesn't just slide down it though. Rings of muscles in the esophagus squeeze the food down into the stomach. When the food reaches the stomach, enzymes and acid are released to break down the food even further. The stomach squeezes the food to help it mix with the acid. We don't have any stomach acid on hand, so we're going to use some vinegar. Next, food passes from the stomach to the intestines, starting with the small intestine, which absorbs all the nutrients from the food. Our small intestines are over 5 meters long, which is the same length as a saltwater crocodile. What's left of the food then moves into the large intestine, where the water is squeezed out of your food to leave a nice solid mess. Now we're just left with the waste, and the waste goes, well, now there are a lot of systems that we haven't discussed here today, things like the immune system, which protect us from disease, or the kidneys, which clean our blood. All of these systems and organs working together to keep our bodies ticking along and to make sure that we survive. But you also have to make sure that you look after your body so that you can live to be as old as Monty someday. Goodbye, everyone.
Well, we're back, everybody. I hope you really enjoyed that. There were fantastic demonstrations from our colleagues there at TechniQuest and Sentinus. And there are science centres in cities all over the country that you can go and visit and experience the absolute magic of science, technology, engineering and maths. Now, what we're going to do, we're going to go on a short break. We're going to have about 15 minutes. So we'll be back just after 12, probably about 12 to start our dedicated secondary session. So we'll see you after the break. Hello everyone. So we're back with our Saturday STEM Spectacular after our break there. And this morning, in our morning session, we've had some fabulous STEM-based activities suitable for our primary age learners. But I bet everybody out there has enjoyed them just as much as I have. And we'll be going out and having a go, even if you're a grown-up. Now we're going to move on in our programme and we're going to start looking at our secondary focused sessions. Now, although they are focused at that particular age of learner, it doesn't mean that everybody isn't going to get something out of them. And I'm sure everybody will enjoy what's coming up because we've got things, we're looking at the human body, we're looking at wrapped up dead bodies, and we're even looking at the jobs that doctors do and all things from physics. So we hope you enjoy the next session about secondary sciences and STEM.
Hello everybody, my name is Tom Warrender. I am the human guinea pig from Medical Mavericks, and welcome to my show where we're going to be using my ultrasound machine to have a look at different parts of my body. We're going to run this as a little bit of a quiz. So what you're going to see on the screen in a few moments are some different scans of different parts of my body, and what I want you to do is write down which part of the body do you think we are looking at. And we're going to use two different probes. We're going to use a flat probe, which looks about 3 to 4 centimetres into the body. These are clues, by the way. And we're going to use our curved probe, which looks much deeper, which is kind of 15 to 20 centimetres into the body. And you'll know you're looking at a flat probe because the image has a flat line across the top. And you know you're looking at a curved probe image because the image has a curve in it. So let's go to our first image, and the way we're going to do this is I'm going to show you the scans first of all, and then we're going to come out of the screen and I'm going to show you where I've put the probe on my body so that you can see if you've got the right answer. So here's my first ultrasound scan, and we're going to start with the flat probe. So here is image number 1. What are you looking at here? There's something quite obvious in the middle. What do you think that is, and where do you think I've put the probe on my body? I nearly gave it away then. I'm going to do something and you're going to see something happen on the screen. Are you ready? Here we go. This is image number 2, and again we're using the flat probe. So what are we looking at here? Looks like there's some movement in there, but not all the time. Image number 3. Here we go. What are you looking at here? And where have I put the probe on my body? So image number 4. We've gone to the curved probe. What are we looking at here? If you don't get this one, you shouldn't be a scientist. Image number 5. What are we looking at here? I'm just moving the probe ever so slightly, so those change you can see just me moving the probe. You've got a massive hole right in the middle. Let me just change the brightness down even more for you. Let's make, there we go, that's a little bit, look at that, that's better. There we go. What do we think that is? And here is image number 6, the last one for you. What are we looking at here? Just looks like a big black circle in the middle. If you watch carefully, that starts to disappear. What could that be and what could be happening? So we've looked at 6 images of the inside of my body, and this is where we put the probe to get those images. So the first one was with the flat probe, and the first one was my carotid artery in my neck, as well as my jugular vein. So the black circle that you can see on the screen, that was my carotid artery, and then when you saw that other circle inflate and just appear on the screen, that was my jugular vein. And I made that appear by just taking a deep breath and straining like I was on the toilet having a poo, okay? So I was like this. And the pressure built up and it filled up my jugular vein with blood as it couldn't flow through properly, so it just backed up and it engorged that vein with blood, and so it appears on the screen. And what you were looking at was an image created by the probe being placed in this position. So it's flat, and it's on my neck in this position. So what you were seeing was a bird's eye view down my neck, like that. So it's like you've chopped my head off and you're looking down my neck, okay? Image number 2 was my muscle in my forearm. So I put the probe like this on my arm. So it's as if you've cut my arm in half like this, okay, lengthways, and you're looking straight through it. And you were looking at the different muscles in my forearm, and when you saw the muscle move, it was just me moving my fingers like so, okay. The third image that you could see were the bones in my index finger, and I just placed my finger on the end of the probe like that and gave it a little wiggle like this, and you could see the end joint of my index finger having a little jiggle around, okay. Image number 4 was use my curved probe, and that one was looking at my heart. And the way I got this image was I popped this under my top, and the probe sat, let me come on to camera on there a little bit more, in that position. So it was looking up. So the image you were seeing was as if you've sliced me like this. Imagine put me through a bacon slicer face first and sliced me in half, opened me up, and you were looking directly on face onto my heart. And hopefully you could see the 2 chambers, the ventricles, and then you could see the other 2 chambers, the atria, and you may have even seen some kind of things flapping around in the middle. They were the valves between the atria and the ventricles. The 5th image that you could see was my liver. So this big grainy tissue that you could see, that was my liver, and those holes were veins that were draining blood, or bile ducts, and that massive hole that you could see, that massive black hole right in the middle, that was my inferior vena cava that was taking blood from my liver and my lower body back to the right side of my heart, okay. And the final image that you could see, that was my bladder full of wee, and as it was getting smaller, that was me having a wee. Now, I didn't do that live, I pre-recorded that video before this. So, where can you find out more information about the amazing careers in the NHS? Well, there are several places you can go, and one of the places I like to focus on is somewhere called healthcare science. So these are not doctors, they're not nurses, they're not physios, but they are a very special set of careers that perform about 85% of all the diagnostic tests in a hospital. And there are about 50 careers in this one sector. Okay, now if you get 5 GCSEs at levels 9 to 4, including maths, English and science, you can go and work in this sector. That is the start point. If you want to look at the different sub areas, you've got physiology, they work with patients every day using things like ultrasound machines. You've got the lab sciences, they work in laboratories. You've got medical physics and medical engineers, they look at imaging, they look at radiation, they look at creating and designing bits of medical kit. And bioinformatics is like the IT side of the NHS. Now, to find out more, you need to go to this website, which is called Health Careers. If you search Health Careers in Google, it'll come up as the first link, but it's healthcareers.nhs.uk. And if you click Explore Roles at the top, what you'll get is this drop-down list of all the different sectors, so nursing, midwifery and all the usual suspects are in this list. But if you go to healthcare science and click that, you get another menu on the right-hand side that says roles in healthcare science. And if you click that one, it gives you these 4 sectors, or 4 or 5 sectors that we've talked about. So you've got bioinformatics, you've got life sciences, you've got physics and engineering in the pink, and then you've got physiology in the yellow. And you can click one of those, and if you click those, it actually gives you a list of jobs in that subsector as well. And guess what? If you click these jobs, it then takes you to another page and it tells you all about the job, how much you get paid, and what you can do to go and get into those roles. Now, there is something really, really important that I need to tell you as well, and is that if you do have students, or if you are a student looking to go and work in the NHS, you need to figure out if the career that you have chosen requires a specific degree to go into it. It's really important that you understand that question, or that kind of statement. Certain jobs in the NHS require a specific accredited degree to go into them. You can't just go and study a general physiology degree, for example, to become a physiologist. You have to study a clinical scientist degree. And I recorded a little video for you to go and watch in your own time to that shows you how to figure that out. And this is how you get to the video. So you need to go to my website, which is medicalmavericks.co.uk, and click the student zone. Now, if you're a teacher, there is a teacher zone as well. You can go there and sign up for a load of resources in our teacher zone, and I'll send you posters and all sorts of goodies in the post and via email as well. But if you're a student and you want to show your students this video, go to the student zone. You then want to go to Medical Mavericks TV. That's MMTV. You'll see it there. I'm dressed up as Gomez Adams. My daughter is Wednesday Adams. That was a little video we recorded for Halloween. And if you click that, you're looking for episode 21. Episode 21 tells you all about how to use the NHS Careers website to figure out if a specific career requires a specific type of degree. And it's really important that you watch that video if that is something that you want to go and do in the future. Okay, now if you go to that website, as I said, teachers, you can go there, go to the teacher area, you can sign up for resources. I'll send you a PDF copy of my book Classroom to Clinic, which is all about careers in healthcare science. You can distribute that PDF freely to all of your students, all your colleagues. There's no kind of restrictions on that at all. You can buy a copy on the website if you want to do, but I'll send you a free copy if you sign up for some resources. There's a medical engineering assembly you can download for free on there, as well as tons of posters that I'll send you over the coming weeks. But I hope you enjoyed my little video exploring the ultrasound machine and having a look inside my body. But make sure you check out those resources with your students and in your own time. And if you've got any questions, just send them our way and we'll be happy to answer them. Until next time, we'll see you again soon. Thanks a lot. Bye bye.
Hello everybody, so my name's Simon Maddock and I'm a lecturer from the University of Wolverhampton. I specialise in conservation genetics, but fundamentally that fits into several other research themes as well. So I'm a tropical biologist, which means that I get to travel to lots of nice warm places in the world filled with huge amounts of biodiversity. One of the things about this is that actually in these tropical regions that are so species rich, they've actually had relatively little research done on them, meaning that we don't know the full extent of the diversity that occurs in these regions. So I'm going to take you through a little whirlwind tour of some of the research that I do in search of these new species. And I'm going to use 4 case examples for this. Firstly, we'll fly to Ecuador and we'll be in the tropical Andes. Then we will fly to India, then to the Kimberley region of Western Australia, and then to a little island archipelago in the Indian Ocean, the Seychelles. Okay. What's really important and what I want to get across to you today is that species discoveries aren't always just going out, crawling through the jungles and discovering something that hasn't previously been described or found previously. That is one way of doing it, and some of the examples that I give to you now will be that way, but other ways are much more experimental in a laboratory or a museum setting. And that's what I'll try to get across to you today, how we go about doing this. But discovering and describing new species is fundamental for all areas of biology. Humans naturally like to name things and put names and labels on things. And this actually, in the terms of biology, is called taxonomy. So taxonomy is the description and classification of groups, so organismal groups, so these animals or plants or fungi, whatever you study, into specific groups. And it's only by doing this that we can understand the diversity that's there, but then it's the way that we can then conserve these organisms as well. Okay, so we'll shoot off now to Ecuador. Okay. So this particular species is Oriama yumborum, is the scientific name, or the Jumbo Riamas. This is a species of lizard that I discovered back in 2011 was the first time that I found it. And this species is a leaf litter specialist, so it actually lives in the leaf litter and is part of the reason why it probably remained undiscovered until 2011. So this is one example of actually going into a rainforest environment, searching through the leaf litter on your hands and knees, or by using a method called pitfall traps. So this is where you dig buckets into the soil and you put a drift fence along this line of buckets, and then lizards and many other organisms, in fact many rodents for example, or other mammals, actually like following lines. So they'll hit a barrier and move along it, and the idea is that they'll hit this barrier, move along it and fall into the buckets, and then we can collect them nice and safely without any harm done to them. Then we'll move on to India. This one is a slightly different story. So this is Certodactylus varadgirii, or Giri's geckoella is the common name. And this is a really, really attractive gecko, as you can see. It's not one of the geckos that you might see on buildings. It is not arboreal, which means it can climb. So it's on the ground, and that is where it generally will remain. It's similar to what you might see in pet shops, or you might have them as a pet even. Things like your leopard geckos. Okay, they don't have the sticky toe pads which enable them to climb up walls and vertical surfaces. So this species was actually known for quite a long time. It was this widespread species where there were museum collections, but this is where one species, they thought it was one species, and actually this Certodactylus group, so that's this genus, is highly speciose, and actually now there have been tens and tens and tens of species described from what was originally thought to be as one species. It's just that people hadn't really looked closely enough to identify that they're distinct species. So the work on this Giri's geckoella was primarily from doing museum collections. So museum specimens have existed for hundreds of years, and we actually harvested and looked at these museum specimens and identified new species from that. That's one example. So two examples that we have given you now for how you can go about describing new species. The third one that I want to talk to you about today is the Kimberley death adder, or Acanthopus cryptomydrus. Okay? This occurs in Western Australia in the Kimberley region. of Western Australia. And this species was known, well, the individuals of this species have been known for a long time, but they were originally thought to be a different species. We didn't even start to look at museum specimens by doing this. What we wanted to look at was genetic diversity across this group, which are the deaf adders, which are a highly venomous group of elapid snakes in Australia and New Guinea. And from doing this genetic work, we actually found that this population in the Kimberley region is highly unique and actually represents a new species. So then we went about the work to describe and acknowledge this new species and gave it the name Acanthopus cryptomydros. So cryptomydros actually means hidden but in plain sight. So this is a referral to the fact that it was always known that that individuals of the deaf adders occurred in the Kimberley region. It's just that we didn't actually know that it was a distinct species. So as I said, there's lots and lots of different ways that you can go about describing new species and uncovering hidden biodiversity. What's really important is that this type of work where we do genetic approaches and morphological approaches, such as with the gecko, that is a lot more common way of describing new species than just rummaging around in a rainforest looking for new species. But it is still done, and it's really important to do that. What I want to show you now is another example. So I'm going to put some gloves on and show you a nice animal. All the examples I've given to you so far have been reptiles. So 2 lizards and 1 snake. Now I'm going to show you some amphibians. Okay, it's really important that we wet our hands for this. Okay, because amphibians have highly sensitive skin. It's very moist. If you've ever touched a frog, you'll know that it's wet on the outside generally. Okay, that is to enable it to breathe. Okay, so they have this. They basically allow this wet skin allows oxygen to pass through their skin. So it's highly important that they don't get damaged from having too dry skins. So this particular animal that I'm going to show you now is an amphibian. It's a type of amphibian that many people have never seen before or heard of potentially. And these are a third group of amphibians. So the first is your frogs and toads, which you might think of. The second is your salamanders and newts. And the third group are these, which are called caecilians. So caecilians. Okay. These are a really cool group of animals. Okay. They have no legs, they have no limbs. So if you think about reptiles, they might be the equivalent of your snakes in your reptiles, so they've lost their limbs. And this is an adaptation to burrowing, so they generally live underground. And there's only a few species that will actually ever come to the surface, so they remain burrowed underground. And you can actually see now, I don't know if you'll be able to see in the video, there's some white stuff coming off this particular organism. These are actually antimicrobial peptides, so they're sort of a poison to ward off any predators. Okay. As well as having no legs to enable them to burrow and live underground, this particular species, the bones are completely covered over their eyes, so they don't have any visible eyes on the outside of them. Okay. Why would they need eyes if they live underground? So many species have adapted to being this, and this is one of the main groups that I study nowadays. Okay. They are a really neglected group. Partly because they're really hard to study, because they live underground. So although I go to lots and lots of tropical places to do work, it's not quite as glamorous as you might think. Well, I find it really fun. It brings in my inner child. So I actually go digging when I'm in a lot of the rainforests that I go to. So I'm just digging holes throughout the forest, trying to find these really elusive organisms. And there are 2 species that I've described so far. The Hypergeophis petit, the petite praline caecilian. and Hypergeophis montanus, the montane marhae Sicilian. Both of these species are in the Seychelles. The Hypergeophis petit, so the petite praline Sicilian, is the world's smallest Sicilian, and it's about that size, fully grown. So really, really small, but really chunky, as you can see. And they've got this really, really cute little face. The little snout is really cute. Similar in morphology, so this is the way that they look, is the montane marhae Sicilian. And this is a really, really important find from a conservation perspective, because the montane marhae Sicilian only occurs at the very top of two mountains that are really close to one another. And because of this, they actually only have a distribution for the entire species of about 1 to 2 square kilometers. This makes them highly threatened with extinction, because as the climate is warming, this means that generally animals that live on mountains will move up the mountains to get to cooler climates. The montane marhae Sicilian is at pretty much the very, very top of these two mountains. So with increasing temperature, it's highly likely that this species will become extinct unless something is done urgently to reverse climate change. That's all from me. Hope you got some appreciation for how we actually go about describing and discovering new species, and the importance of doing so from a biological and a conservation perspective. Until next time, see you.
Hello, I'm Chris Hamlet and I represent a group called Discover Materials, whose aim it is to promote materials science. I'll talk a bit more about that group later. But firstly, what is materials science? Is it chemistry? Is it physics? Or even biology? In fact, materials science is concerned with aspects of all of those three sciences. Firstly, chemistry allows us to control the arrangement of atoms and molecules, which are the building blocks of materials. Physics sets the laws that govern the behaviour of these materials, so how strong it is and how it conducts electricity or heat, which is really helpful when you've got a coffee cup such as this. I've got boiling hot liquid in there and my hand's not burning. And biology dictates how a material interacts with living systems. But it's not just the three main branches of science that are part of material science. It's also engineering and design. For example, making smaller and smaller devices to fit on a computer board. The smaller the device, the more you can fit on a board. So you get faster and faster computers. So that can't be done without, again, a mixture of chemistry, physics and engineering. So material scientists have come up with some fantastic materials. From the everyday, for example, this mug. If you think of this mug, it's made of ceramic, it's cheap and easy to produce in bulk, and it's strong enough to hold its shape when liquid is poured in. And also it's a poor enough thermal conductor so that you don't burn your hands while holding the mug. This is a paperclip. However, this paperclip, when bent out of shape, can have its shape restored by just putting it in hot water. So this is made of an alloy called nitinol, which is about 50% nickel, 50% titanium, and has been developed for things like stents for blocked arteries. Ooh, look at the mug. It's changing colour. And you can see that there's a picture on there.
So the picture on that mug is coated in what's called a thermochromic material, which is a material that changes colour in response to heat.
Material scientists get inspiration from various sources, such as global problems of recycling plastics and batteries, through to just pure and simple curiosity of the world around them.
There are many amazing surfaces in nature that have inspired new materials. Let's have a look at some examples.
So if we're going to examine a surface and see what it looks like, we could use a magnifying glass. However, magnifying glasses can only give up to about 70 times magnification. So you could use an optical microscope. These give magnifications up to about 1500 times. But however, if that's not enough magnification, you'd have to move to an electron microscope. Electron microscopes use a beam of electrons to fire on the surface, and you can do this in one of two ways. Either by the beam coming in and scanning across the surface, so that's known as scanning electron microscopy, and can give magnifications up to about 100,000 times. Or you can fire a beam of electrons through a sample, and this is known as transmission electron microscopy, and can give magnifications up to about 1,000,000 times. And transmission electron microscopes can actually see atoms. So this image here is of a single strand of DNA, and you can pick out the individual atoms in that image. So we're going to investigate two surfaces found in nature using a scanning electron microscope, and these images were kindly taken for me by the company Zeiss. So the first surface we're going to look at is that of the lotus leaf. So the lotus can be found in slow moving rivers and deltas in India and other areas of southern and eastern Asia. And it's got a remarkable water repellent property. So if we try to wet it, the water skids straight off. And this is because the surface of the lotus leaf is made up of a naturally occurring wax. However, not all waxy leaves have got this water repellent property. So if we try to wet this holly leaf, you can see that it's a bit water repellent, but it doesn't skid off in quite the same way as the lotus leaf. So let's look at the surface of both the holly leaf and the lotus leaf using a scanning electron microscope. So this is an image of the holly leaf. You can see it's fairly featureless, fairly flat, at reasonably low magnification. And if we increase the magnification, we can still see that there's not that much sort of surface texture there. Whereas at the lotus leaf, you can see it's got this like bumpy structure on there. And if we zoom in even more to these bumps, you can see that these bumps are made up of tiny little straw-like structures. And this gives it a huge surface roughness, and this is the main difference between the holly leaf and the lotus leaf. So why are these bumpy structures so good at repelling water? If we use this Duplo model to think of the lotus leaf, it's got bumps like the lotus leaf, and on these bumps there's another layer of roughness, some more bumps, which are like the straw kind of structures you saw on the lotus leaf. So this is known as a hierarchical structure, and if you imagine this is all coated in this naturally occurring wax, which water doesn't like, and this balloon is a water droplet, it rolls around really easily on this surface. But as you can see, it doesn't actually touch the bottom of the valleys in between the bumps. So this is due to the surface tension of water, or in this case the balloon's skin. And this means there's very little contact between the water droplet and the leaf, and so it can roll around very easily. So the lotus leaf has provided inspiration for development of non-wetting water repellent surfaces, such as paints and water repellent fabrics, such as these swim shorts. So if you can see, the water just skates off and doesn't wet the fabric. So let's have a look at the swim shorts under the scanning electron microscope. So as you can see, they're meshes of fibres all woven together. These are actually polyester fibres, but they're coated in a water repellent chemical. So like the lotus leaf, you've got the bumps from the thread and the water repellent chemical coating. So we can see the water just rolls right off the shorts on basically a cushion of air, and this air is trapped between the water droplet and the fibres.
So this is a morpho butterfly. It's found in South America and it's got an incredible iridescent blue colour, and this is all down to the surface structure. So this hierarchical structure is made up of scales, and on these scales are ribs, and these ribs are made of micro rib structures, and all of these act as little mirrors to reflect the light, which interferes with each other, allowing only the blue light to reach your eye. Okay, so that brings to an end our journey through an SEM into the wonderful surfaces found in nature. So I'd like to finish by thanking Ken and Romana from Zeiss and Amy from University of Birmingham for wonderful SEM images. I'd like to point in the direction of the Discover Materials homepage, on which you can find information about our upcoming winter event. And also in the new year, this will be where you can find all of our wonderful content for our new look website. Here are SEM images of 4 different things. You've got to guess what they are.
I'm Professor Richard Johnston from Swansea University, based within the engineering department, but I'm a material scientist and engineer, mostly working on imaging, characterization using microscopes, and I apply that to the human-made world, but also the biological world around us, and sometimes historical artifacts, like the Egyptian animal mummies that we're going to look at today. Okay, as I mentioned, I'm from Swansea University, and I run an imaging facility. And we're going to look at these animal mummies and how we work on those. But firstly, it's important to point out that the science and research I'm talking about is ongoing, current. Some recent bits have been published, but it's a team effort. And so it wouldn't be the same without the Egyptologists, the zoo archaeologists, the biologists, and the material scientists and microscopists. And we all come together bringing our expertise. And pretty much any science you hear about currently will be a team effort of people with diverse backgrounds, diverse experience, bringing different things to the research. So we all have our own expertise and link in together. It's important to also respectfully acknowledge the people of ancient Egypt who created these artifacts that we're going to talk about today. So thousands of years ago, these were created by people, and we're using technology to try and understand them in a new way today. And as I said, we're going to look at animal mummies. So we're going to look at how we use modern day technology to reveal something that was created thousands of years ago, to be the first people in 2000 years to see the inside of these mummified wrappings. Very briefly, what are animal mummies? So I'm going to be talking about things that are around about 2000 years or older than 2000 years old. And there were 6 categories roughly of animal mummies, and I'll run through those very, very briefly, just to give some context. So some were pets buried with their owner. Some were victual mummies, that means for food, kind of in the afterlife. Some were sacred animals, which were worshipped during their lifetime. Others were votive offerings. That means they were offerings in burial processes, and they depicted the gods and were placed in temples as offerings around that time. Others were false or amalgams. So that would be potentially you have a mummified package, but nothing in there, or bits of bone from something else. So not necessarily false, but they weren't what they were represented to be. And then a 6th category of other. But we're going to focus on votive offerings, these offerings to the gods. So these were produced in the late period, so over 2,000 years ago, and it's estimated that there were over 70 million animal mummies produced, which is like staggering. That's a huge number. That's more than the number of people who live in the UK currently. So, 70 million, imagine that. That's a huge number. And these were given to gods, and certain animals were acceptable to certain gods. But, we're trying to think of 70 million. That's a gigantic number. And so that requires almost industrial scale rearing of animals for the process of mummification, and then industrial scale mummification processes as well. And when you imagine something that large, then you get society and practices that are developed around that. And so produced in a certain way, and society builds themselves around such an activity potentially. So mummified animals can give us an insight into society of the past, not just of this animal and what's inside those wrappings. And so, comparison to modern day, you might think 70 million animals, oh, this is, being reared and mummified is, that's not nice to hear about. But actually, we look at our current practices as society today, and we can consider how perhaps not ideal those practices are in terms of animal welfare. It's a good time to point out some researchers in this area. I'm a material scientist x-raying these mummified remains, but you also have Professor Salima Ikram, who's an expert in animal mummies and has a show on Netflix at the moment, and Dr. Lydia McKnight, also an expert in animal mummies and imaging as well. So we're going to use x-ray vision. That's what I've used to look at these animal mummies and to try and show something different. So that's the skills and the capabilities we have in our department. We have the ability to use x-rays to look inside things. And so firstly, mummified animals and mummified remains, were beginning to look at them in the 1800s, but most of the techniques were invasive or intrusive. And so you'd have a mummified package and it would be unwrapped by hand, which is a destructive process. Then came along x-rays and the development of x-ray imaging to allow us to image large-scale human mummies and then animal mummies. So this is an example of a human mummy, an x-ray through the coffin, effectively, and you can start to see loads of interesting things, really interesting insight into that mummy without destructively unwrapping it. But it's low resolution. For animal mummies, that doesn't really cut it. And so that's medical x-ray CT. That's those big circular tubes where you may have had a medical CT or know someone who's had a medical CT scan. What we use is microtomography. And so this is an example of X-ray microtomography where we effectively reveal the inside of something non-destructively, but we do it on small things. And so we talked about that whole animal mummy, that would be a whole human mummy, that would be rather large. But what we can do is something like this. So this is an example of a chocolate egg with a toy inside, where we're able to X-ray the inside of that, look at that structure inside, digitally remove the chocolate and the plastic that's around it to study that bear, in this case, inside. And I still have this chocolate egg toy thing in the lab intact. I could take it back to the shop if I wanted to and get my money back. But effectively, that's what we're able to do with X-ray microtomography. Look at small things inside other containers and be able to study them. And then what we can also do is take that and 3D print the insides. So from this Kinder Egg, I was able to take the toy out digitally, and I can reproduce this. I've printed hundreds of these bears, and I've never opened that chocolate egg toy. But how does that help us with mummies? So on the left, we've got an example of a mummified package from the Egypt Center at Swansea University. To X-ray that, we'd see the middle image, which is just kind of X-ray through, but we can't really tell what we're looking at. And then X-ray microtomography is 3D X-raying. And so that video on the right shows us digitally removing the wrappings to show this coiled snake inside. So why do we do that? Why are we using X-rays to look inside things? Well, firstly, it's non-destructive. So that package has remained so for 2,000 years. So we shouldn't really come along and unwrap that package and destroy the wrappings. And so with this, we've got X-ray imaging that's non-destructively looking inside. But it's just a tool really to help reveal those stories of the past. And we teamed up with the Egypt Centre, a museum in Swansea University, which had these artifacts with our collaborators there. And I also have this imaging facility on the same campus. So the Advanced Imaging of Materials facility, we have all of these techniques which we can throw at various materials, from jet engines to animal mummies. And it's about curiosity. Who doesn't like looking inside something that no one has ever seen for 2,000 years? But it's also about interdisciplinarity and these characterization tools. So can we tell stories of the past using all of these things? So it started with the snake. We firstly had this package. The Egypt Centre had taken it to a vet years ago and had this 2D X-ray image, which is okay. It shows it's a snake. And we put it in our X-ray microtomography machine and we can see it's a snake again. But the key thing is we do that in 3 dimensions. So rather than just this 2D image that you can tell is a snake, but you haven't got the positions of any of the bones, there's no context to that. We now have this 3D image because we've rotated our sample while X-ray imaging, and we can generate high resolution 3D data. So we have this now. We can digitally unwrap non-destructively, so we're not breaking it. We digitally unwrap this mummified snake to try and tell us more. And from that, we were able to have, this representation. It's still intact in the museum, but we can zoom into certain bits and we can identify possible cause of death of the snake 2,000 years ago. And so we've got this separation of the vertebra, and we think that's through a whipping action. So, you take a bull whip or just a whip and you whip it. That's a method of killing snakes even today. And so you whip them and it effectively fractures the vertebra and kills the snake. So we think, thousands of years later, we've identified a method of killing them. And then we wanted to zoom into the head. So we need to get inside even closer to look at some of the structures within the head and to help us identify the species. So we can zoom into the head. And we do that, and it gave us this whole new data set, another 3-dimensional data set at higher resolution, where we've got the head structure. We can see damage to the head that's happened through the process. Our biologist, Dr. Rhys-Jones in Cardiff, was able to identify the species as an Egyptian cobra. So now we know the species. We know potentially how it was killed. And also these other furry structures here are calcified kidneys. And so from that, we can identify that it was potentially dehydrated before its death, which can give us insight into how it was kept. Maybe it didn't have enough water at the time, because snakes drink water, which would have led to dehydration and calcification of these kidneys. And so we get the species identification to be an Egyptian cobra. We have these calcified kidneys, which showed up clearly within the X-ray. We also identified these structures within the mouth, which have a very precise placement, which potentially suggest a complex mummification ritual as well, which hasn't been seen before in snakes, all through being able to do this high-resolution X-ray imaging. And then I can take that data again. So we have our 3D data, and I can put that into virtual reality. So I can effectively put myself within the 3D data. And so in this view, you're seeing the view from my 3D VR goggles, and I can make this snake skull as big as my house. And I can tour around that snake. There's a good video next. So I can tour around that snake. I can go inside the skull and look at the organization of the skull. I can look at all of the fractures and how they may have happened. And I can find these tiny, tiny inserts. Because this skull in real life is about the size of my thumbnail. It's a really small, quite a juvenile snake, but I can make the skull as big as my house. I can crawl through the vertebra of the snake and come across that fractured part where effectively it was whipped. And here I am inside the skull of the snake. Then I can take the data and I can 3D print that. So now we have something that's still inside the wrappings, but I can hold it and I can touch it, and that can help me identify the species of snake as well by being able to feel the ridges of the bones on the skull. And we can print that even bigger. And so the skull is this big, but we can 3D print something this large, and it just represents it in a different way, enables us to see more. And so we've identified the possible causes of death, possible conditions while alive, some of the mummification processes. We've identified the species as an Egyptian cobra, and some of the ritualistic practices at the time. So what else can we do? We can look at some slightly larger mummified samples, but what can you do? So you could explore this data at home. So we've put the 2 data sets, simplified data sets of the snake skull, but also a mummified cat skull onto somewhere called Figshare. So you can move those around and manipulate them and make them bigger on your screen. And if you've got a VR headset, you could make them as big as your house and crawl within them. At this point, it's crucial to acknowledge my cat, who was very, very helpful when we were analysing mummified cat skulls, so I could quickly measure her head and compare it to the mummified cat that we were looking at. And it turns out that it was a kitten. It was a lot smaller than my cat. But also the Egypt Centre at Swansea, visit the museum if you're able to. And that's that. That's the end of that. So thank you. Hopefully you found that interesting. And yeah, I'll leave it there. But that's mummified animals with X-rays.
Hello there. I am Fabrice Lossi. I am Professor of Physics at the University of Wolverhampton. I am Chair of Light Matter Interaction there. I'm also the course leader of the physics course, and I'm teaching myself several modules. So if you come to do physics with us, you'll get to see a lot of me. Not only me, of course, lots of very interesting colleagues from all over the world, actually. Britain, of course, but also Spain, Colombia, Russia, lots of different places, lots of different cultures to learn about these topics, which is to tell you about the world itself. The world physics is the science of the universe around us. Let me give you an example of the type of things that we study in physics. A very revealing one, because it will, in one particular case, it will show you what we have in mind when we think about physics. This is this one, the rainbow. Rainbow, you've all heard about it or read about it. There are songs, there are stories, there is a full chapter in the Bible about the rainbow. How do we see the rainbow ourselves as a physicist? Very different ways to understand, to see the rainbow. The mathematical structure to start with. Physics is like using math for the real world application. So if you like everything that involves mathematics, then what you can do is pure mathematics, of course, abstract mathematics, which is also very interesting. Or you could look at mathematics from the point of view of engineering to build things. But more interestingly, from my point of view, because that's what we do, of course, is to use mathematics to understand things that are outside. In the case of the rainbow, for instance, how would we describe this object? Well, you see, it's an arc. We speak of an arc for the rainbow, right? Actually, it's not an arc; it's a full circle. Right? We don't see the circle because, of course, there is something which hides it. Here, I show you a rainbow where you can see the full circle of the rainbow. And when you've got the circle, you've got two things, right? You've got the radius and the center. So let me tell you about the center, for instance. A very beautiful thing that you can check next time you go outside. The center of the rainbow is cast by the shadow of your head. It is your eyes are the center of the rainbow. So where the sun is putting the shadow of your head, that's where fits the center of the rainbow. Which means that it's a virtual object. It's not something that exists. It's something that your mind is reconstructing. Different people will see the rainbow in different places. So there's no way to go at the end of the rainbow to find the pot of gold, of course. When you can't find this in books, but in the real universe, you will not find that. And what causes the rainbow? This is the so-called diffraction. It's a process of light that enters into the little droplets of water, and then light dispersed there. It gets separated into its different color, different frequencies, and because it's bouncing back and forth inside, it can also escape, and we've got this beautiful spectral decomposition of the rainbow. It's something that was discovered by a great scientist of your island in UK, by Newton. He was the one who first described this phenomenon, and he used it to make his theory of light in his very famous book Optics, the first scientific book written in English. So I gave you the example of the rainbow, but we could take virtually every possible example. Like I like a lot as well the case of Eratosthenes. He was this librarian. We were not speaking of physicists at the time. He was the head of the library of Alexandria under Ptolemy, and he had heard about this story that in Siena, which is one island in the south of Alexandria, it's called Aswan nowadays, I believe. He heard there the story that there was one day in the year where the light was radiating from the wells. Right? So he understood that instead of making poetry out of it or something mystical, he understood that light was radiating from the well because the sun was directly overhead. Right? So the sun was beaming like a beam on the bottom of the well, and the light were just being reflected. But more importantly, when he understood that, he also realized that no such thing was happening in Alexandria. So there was something different. And what was different is the curvature of the earth. Never was the sun directly on top of Alexandria, so that has to cast no shadow. So then, by very elementary trigonometry, the science of the circle, the relation of the triangles in the circles, he understood that if he was able to measure the length of the shadow in Alexandria when there was no shadow cast in Siena, then he could indirectly work out the radius of Earth. We are speaking of 6th century before Christ, a long time ago, right? We had nothing at this time, no cell phone, nothing, right? And already, no satellites, of course, there was no way to even know, for sure, to have direct sighting of the curvature of the Earth. But by this very little understanding, this modelization of the shape of the Earth, he was able to make this measurement. To make the theory of this measurement, because he didn't himself make the measurement. What he did is to ask people, he gave the instruction to carry out the way to find this. The story says that he asked someone to take a camel and walk all those distance from Alexandria to Siena to count how many camel steps there was in between, and from the knowledge of this arc again, he could, using this formula you see on the screen, he could work out the radius of the Earth very accurately, actually. So here you've got another example of what physics is about, like by an epiphany, like an observation, an understanding, an eureka moment, like I understand in Greek. Then you connect a shadow to the cosmos. Many people did that. Again, endless of examples. Newton with the apple that falls, and that's how we understand gravitation and the orbit. So Einstein with his examples of the this so-called Gedanken experiment, the thought experiment. Things you cannot do but that you can imagine. He understood the nature of space-time and he explained to us, and now we can make experiments, that things like time travel, they are actually not science fiction but physical reality. You can actually travel in time. The trick is that you can only travel to the future, not to the past. Again, it's something that we can check on an everyday basis, where we check it ourselves in our laboratory. We run experiments in Wolverhampton, as well as doing all these Gedanken experiments and this math on pen and paper. So we show you, for instance, that you can detect muons in Wolverhampton. We detect the muons, despite the fact that these muons, they are created very high in the atmosphere when the cosmic ray is hitting a nitrogen molecule, and they have a very short lifetime. So even going at the maximum speed which is allowed, which is the speed of light, they live so little time that they wouldn't have the time to reach us on the at the Earth level in the laboratory. So why can we detect them anyway? It's because they are actually going so fast that they go into our future. Their time stretch, and they see the time, by the time dilation effect of special relativity, they're able to extend artificially their lifespan. So if you would do the same with people than we can do with muons, which means that you would just send them very fast, you put them on a rocket that goes as close to the speed of light, we would be technically able to send these people into our future. So you can take your little cousin with a small baby now, and he would come back from this superluminal, well, from this trip that goes at almost at the speed of light, he will come back being older than you are. These are things that you might be familiar with, for instance, from the movies, right? It's people that grow in the course of a few hours, they grow 20 years back. So all this is true. Just it's not science fiction. It's true as long as you understand in which context, in which case it is true. So what we do in physics is precisely that, is to play with all these beautiful ideas, not only relativity, but also things like quantum mechanics. This is even more interesting because that goes crazy. Here there is no limits to what you can do. You might have heard about the Schrödinger's cat. This is this concept, this idea, which again is a real physical reality of something that can be simultaneously in two different states. So in the case of the Schrödinger's cat, it can be both dead and alive at the same time. Really strange, but this happens. We can do it as well in experimentally in the lab. Not in Wolverhampton, because it's very difficult to do quantum experiments, but we do a lot of theory on quantum mechanics. We explain you like things like quantum teleportation or quantum computations, a lot of very beautiful effects. We are also very research active, which means that we like to investigate things that nobody knows, and we involve our students in that. So if you are interested in doing research, it's especially in the topics of quantum optics, physics of lasers, these kind of things, it's a very good place to come, Wolverhampton, because we have some of the best world experts on these topics. We have people who work on topology, we have people who work on multiphoton emitters, lots of different activities. So I hope I gave you more or less a rough idea of what physics is about. If I should have to summarize my little talk in a few words, I would say it's It's fun, it's interesting, and it's versatile. It concerns everything. Like, everything is a particular case of physics, chemistry, mathematics, even things like biology or even medicine, because we start to see more and more things like biophysics or the equipment you need, like the MNR objects to make some scanning. They all come from concepts of physics. So the physicist is more and more thought on the marketplace, and in Wolverhampton we are at the edge of what is trending in physics nowadays, so it's a good place to come and speak with us, come and do physics with us, have fun with us in Wolverhampton.
Hi everyone, my name's Abby and I'm a second year medical student at the University of Warwick. So that means one day I'll be a doctor. And that day is a lot sooner than I care to think about. So when I first started medicine, I didn't know how amazing the human body was. I knew a little bit about the brain, but even in my 2-3 years in medical education, it still surprises me today just how our body can change, adapt and function. And I'm going to give you a few little did you knows today and teach you some cool tricks to do with your body. So let's get started. The brain. Of course I'm going to talk about this. I think brains are amazing and they're part of the body that I've been obsessed with for nearly 10 years now. The coolest part of the brain is actually that you can take one half of the brain out, especially when you're a kid, and you'll still function normally. Unlike taking half of your heart out, the brain can actually cope if you take half of it away. This is something what we call neuroplasticity. So if you think of a brain being wired like a light bulb, the wires just go a different way and they form different connections, meaning that we can still function without half a brain. For most normal people, however, you kind of think we only have one brain. But you're kind of wrong. You see, here we have our brain. We have the brainstem, and then at the back, so at the back of your head, we have something called the cerebellum. Now, cerebellum literally translates to little brain or small brain. And this is because the cerebellum actually, although it largely controls movement, it does have some function of every single area of the brain. So next time someone says, oh, you don't have a brain, agree with them and say, no, I don't have a brain. I have two. Oh, just getting myself a snack. Now, when we eat, you probably know that our tongue has taste buds, and these taste buds pick up different tastes. So, we all think, I've done this now, the end of the tongue picks up salty things, and the back of the tongue picks up bitter things. What if I told you you were wrong? In fact, every taste bud on our tongue can sense each different taste. We have sweet, we have salty, we have sour, we have bitter, and we also have another taste called umami, which kind of means meaty and savoury. So that means that when I eat my cracker, I'm not just tasting it in one area of the tongue, it's my entire tongue that's eating. Pretty good job, really. Now, I could stop talking about brains, but why would I want to do that? Your brain is that adaptatious. But if you hung upside down like I'm doing for a couple of days in a row, although I wouldn't recommend it, your brain will actually flip around the vision from your eyes. So you'll start seeing everything the right way up again, even if you're hanging off the ceiling like a bat. I'm stuck. Eyes. They're pretty weird, but they're also kind of cool. We all know our pupils change according to the light we're in. So if we're in bright, they go smaller. If we're in the dark, they grow bigger. Now, when we do this, we all look at the pupil we're shining the light in. But have you ever looked at the other pupil? Let's do this now. Come a bit closer. So I'm going to shine the light in this pupil here. I want you to see what happens in this one. So let's go. Did you notice that? The pupil that hasn't got the light shining in it is still adjusting to the brightness levels of the other eye. This is an amazing trick that your brain does to stop you having blurry vision. After all, we want our eyes to be looking in the exact same direction at all times of the day. Otherwise, this creates a double vision where your brain can't piece together the two images from your eyes. Now, my brain's slightly different. I have something called a lazy eye and astigmatism, where my lens of my eye, where the light goes through, is slightly rugby ball shaped, so the light tends to get blurred. However, my brain has adapted around this when I was little, and through neuroplasticity, which we've learned before, and actually I use this eye for all of my sight. I can see peripheral vision in this eye, but if I was to lose my good eye, I would actually be legally blind. And that's how amazing your brain is. Book time! Now, as a medical student, I read a lot of textbooks. Too many textbooks, but we'll leave that fact for now. However, my whole journey started out by reading this one book. It's called Blame My Brain by Nicola Morgan, and it's the whole reason I love brains so much. There's so much in here to explain how your brain works, and particularly if you're year 6 or year 7, it'd be really interesting because it tells you what your brain's going to do in the next couple of years. So that's my recommendation. Oh, sleep. I can't get enough of it. I could sleep all day. But do you know why we sleep? It's because towards the end of the day, our brain starts releasing a molecule called melatonin. And this means that we start to feel sleepy. Well, we should do. Unfortunately, with the kind of development of mobile phones, iPads and laptops, they secrete something called blue light, which stops our brains releasing this melatonin. So if you struggle to get to bed at night and struggle to get to sleep, I recommend popping your phone away, grabbing a book and having a read. As satisfying as TikTok can be to scroll through, it's not the best thing for getting a good night's sleep. And that's really important. Even at the age of 23, I should be getting about 8 hours sleep at night. Sometimes I don't get that, and sometimes I get too much. But it's fine. So, I'm going to go to bed now. I hope you guys have a fantastic rest of the year. It's nearly Christmas and we're nearly at 2021. Just a couple more sleeps to go. Night.
Well, everyone, I hope all of you watching right now, and thank you for those people out there that have been with us on this whole journey through science, technology, engineering and maths. I hope out there your mind is as blown as mine after seeing some of those fantastic presentations that we've just had by our experts. Now, what I will say is that we're going to move on to our panel discussion now. But before we do move, I'd just like to thank particularly Tom Warrender and Chris Hamlet for answering the questions that have been on our chat. So we are going to move on to our panel discussion now. And this is where we got 4 experts from a variety of different subject areas to actually answer the question, what could they learn from the natural world? Now, this panel is chaired for us today by our Pro Vice Chancellor, Professor Nazira Karodia.
Welcome to the Saturday STEM Spectacular and this panel discussion. What can we learn from the natural world? I'm Nazira Karodia, the Pro Vice Chancellor for Regional Engagement at the University of Wolverhampton, and I have a fantastic expert panel with me today. They are Jack Sharp from Greenpeace, Elise Jander, primatologist, Belinda Rich, advanced materials for space habitats, that's her specialism, and our own Mark O'Shea, herpetologist. What I'm going to do, panelists, is ask you to present a short presentation, and then we will discuss the key points that you will raise and that come through during our discussions today. We'll start off with Jack. Jack, are you ready to launch into this discussion and do your presentation?
Yes, absolutely. Thank you very much for the introduction, and thanks for the invite. It's great to be here. So what I think we can learn from the natural world, coming at it from a purely environmentalist perspective, is the interconnectivity of the natural systems, and also the fact that nature communicates directly with us. So I'm working for Greenpeace in Scandinavia, across the Nordics, and we have a phrase here which says, "What happens in the Arctic does not stay in the Arctic." And what's meant by that is there are many things going on here in this very, very fragile and vulnerable region, both in terms of inputs and in terms of outputs. So in terms of outputs, what's happening, there's a lot of talk at the moment, a lot of expansion of the oil drilling and the shipping industries in the area. And when we say what happens in the Arctic does not stay in the Arctic, means the effects of these invasions and exploitations of fragile areas are felt around the world. So what starts as a local issue often becomes global if it's left to go too far. So this is actually true for all natural systems. If there is large-scale destruction of forests or abuse of the oceans in terms of overfishing, in terms of pollution, etc., these may start off as local issues right outside your back door, but actually they evolve into great problems potentially across the world. So, being that everything is connected, what does that actually mean? Like, how does this happen? The fact of the matter is that nature has evolved in balance. So, all the systems that we have around us have developed alongside us and alongside each other. Nothing is separate, nothing exists in a vacuum, and everything has the potential to affect everything else. So simple ways you can see this are through, for example, bees and their relationship with flowers. So obviously the flowers provide food and sustenance for bees, and also the bees provide a welcome service for the flowers when they attract pollen whilst they're feeding, and spread that across vast areas on many occasions, meaning that the flowers themselves can propagate themselves and continue to develop and evolve in their own ecosystems. So when we take that as an example, we can actually apply that to ourselves. We shouldn't ever forget that we are a part of nature as well. We're not separate from the systems in which we live. We're not separate from any of the ecosystems. So how does nature communicate this to us? This is obviously a really key thing. If you consider the fact that everything is interlinked, we can also almost be treated as if the whole natural world and all of the ecosystems are part of a single body. So if we have too much input into our bodies, we develop symptoms which may at first seem unrelated. So for example, if you have too much sugar, it could affect your skin, etc., etc. The natural world exists in the same way as this. That's how nature communicates with us. When we see these strange outputs, we must be aware that there has been an input. So for example, at the moment, we're seeing a huge increase of extreme weather events, of strange unseasonal migrations of populations, coral bleaching, for example, mass die-outs. These all may seem completely independent events, but when we understand the interconnectivity of nature, we must realize that they're not. They're actually nature communicating with us and saying that there are some causes which are causing these effects, and that they're not separate. And that's one of the key things that the nature can communicate to us. Of course, as well, the events that happen, the effects of these damaging causes, can themselves cause an acceleration of other causes. For example, whilst the emissions coming from exported oil from the Arctic, for example, can cause heating, which creates the conditions possible for increased forest fires, which in turn release a lot more carbon, and the cycle continues. So it's very, very important that we actually listen when nature tries to communicate with us and tries to expose these issues to us on a fundamental level. And the next question then comes, how do we respond to it? Well, the first thing is education. We need to understand that these are not standalone events. They're symptomatic of a much, much broader problem. The causes may seem distant and unconnected at first, but when we realize the symbiotic nature of the natural world and the ecosystems, and the fact that everything relies upon everything else, and we apply the simple cause and effect model, it tells us that these things are not unconnected. And in order to respond to those, we need to essentially reconstruct our relationship with nature, remembering that we are a part of nature. We're not removed from these effects. We're not removed from the causes. So we really need to develop our relationship again with the natural world. And we can do that through many, many different ways. So at Greenpeace, for example, we carry out investigations into these effects that we see, discover the causes, expose those responsible. If that is the case, it's often the case that there's an industry or an exploitative organization behind these causes. And then we act and take action to protect the natural world as it stands and to prevent these things from happening in future. So this is something that's just one way of doing things as an organization. I think the most important thing about this is this interconnectivity with nature and responding to what nature tells us, is that everyone has the ability to do it. What happens in the Arctic doesn't stay in the Arctic. What happens at home for you, wherever that home may be, doesn't stay at home. So when we're faced with these big, scary global problems, the most important thing to do is to realize that we shouldn't be afraid of them. If we do what we can, where we are, to reconnect and respond to nature, we can make a real difference. Because what we do, where we are, can affect the ecosystems that we have a relationship with. So yeah, a wise person once told me, if you keep the small fires burning, one day you can set the world alight. And I think that's a great ethos to live by. And don't be scared by the big terrifying things. Just remember that we're all connected. We're all in this together. We are a part of nature, and we can solve these problems as one. I think that's about it from me.
Thank you, Jack. And I think there's some key points there that will be of interest for picking up in terms of how do we get connected if we feel that disconnect. So we'll pick that up later. I'd like to now welcome Elise Jander, our primatologist on the panel, to give a presentation.
Hiya, thank you so much, Nazira, and everyone else for organising this, and thank you again for inviting me. So yeah, I'd just like to talk a bit about, firstly, what primatologist is and what I do. So when we talk about primatology, we're actually talking about the behaviour of primates. So the study of the behaviour of primates. And primates are a group of animals. They're an order of mammals that have opposable thumbs. So we also have opposable thumbs, and that means that we can move our thumbs around. For example, animals like cats and dogs, they have the paws. They have their thumbs still, but they can't move them like we could. I'm sure they'd cause lots of havoc if they could. So these primates are a group of mammals, and it's a huge group of animals. So this covers your lemurs, your lorises, your bush babies. It covers your monkeys, your well-known ones, such as like your baboons and your macaques. And it even covers your apes as well. And there's 5 species of apes. These are your gibbons, and then you have your great apes, which are your orangutans, your gorillas, your chimpanzees, and bonobos. And we refer to all these animals as non-human primates. And we do this because as humans, we're in this group of primates too. So we are actually primates. We're part of the great apes. And we actually share almost 99% of our DNA with chimpanzees and bonobos. So it makes us really, really closely related to each other. And by looking at nature and by looking at the behaviour of these other primates, we can kind of have an insight into our own development. So we can see, by looking at how apes evolve, we can also see the evolution of ourselves. So how our societies evolved, how we learn, how we construct cultures and societies. And that's what I really want to talk about today, is looking at, well, if we look at nature and the animals in nature, how we can also use that to reflect upon ourselves. So like I said, humans are one of the most successful primates, or the most wide-ranging primate in the world. We're found on every continent. And because we're so wide-ranging, there's lots of populations of us, and that means that we have lots of different cultures too. Now, the word culture, you might know what it means, but I'll just sum up for those who might not know what the word culture means. For someone to have a culture, it's just a different way of thinking or acting or behaving, just because that's what you know, it's a norm for that culture. So for example, this can mean like the way different schools in different countries teach their children, so the education systems, and a more common one, the way and how we celebrate New Year, for example. We celebrate New Year, obviously, at the end of December, but you have Chinese New Year's and other New Year's, and we do this all differently just because of our culture. So what we've learned from our parents and their parents was just been passed through generations. And it wasn't only until, I think it was the 1960s, we assumed that culture was specific to humans only. So humans having culture is what set us apart from other animals. It's what set us at the top. But recently, like I said, in 1960, we changed our whole perspective of this. So one of the great apes, the orangutans, it was saw that they started having their own culture. So lots of scientists and lots of primatologists got together. They started researching and studying the behaviour of many populations of orangutans. And what they found was actually really interesting. So they found that different groups and different populations all did slightly different behaviours. And they found about 24 behaviours that differed between these groups. So, for example, when orangutans go to bed, they make nests, but between populations differed on how they'd actually made the nests. So one population would make them out of a certain material, another would use another material, some would be higher than others. They also found that some populations said like good night to each other by blowing a raspberry, and that wasn't seen in other populations either. And one of the most critical things that was saw was the use of tools. Now, when we say tools, obviously we don't mean like hammers and saws like humans use, but we define tool as an item in the environment that gets used and manipulated to help certain behaviours. So one of the examples, orangutans were seen using little twigs and sticks, and what they would do, they would get their stick and poke it into termite mounds, and the termites would come up and the orangutans would be able to eat them. There's even evidence a few years ago of orangutans using big sticks to help in not fishing, but fishing items out of rivers. So they're really coming on and advanced. And the really special thing about tool use is obviously it's not something that every animal does. It's not something that they're known to do. So it's created through trial and error. And then once it's successful, that behaviour is then taught taught between mothers and parents and children, and it goes down through generations, and it's what we call a learned behaviour. And learned behaviours are crucial for defining culture. As I said, culture is passed down through generations through learned behaviours. And it's not just orangutans we see either. There's many different primates that we now find to use tools, including chimpanzees and bonobos again. This started off with Jane Goodall in Gombe. So she saw some chimpanzees using grass blades again, just to dip the termites. But they've also seen chimpanzees actually break branches off trees, break them into different sizes and different thicknesses, pull the leaves off. So they're actually starting to manufacture their own tools too, which is a great step if you think about it in terms of like intelligence from an animal. And all these things, like, again, it's just reiterating, it's a behaviour that's trial and error, and then when it's successful, it's passed down. So it's a learned behaviour, and that is a defining feature of culture. And that just shows that we can learn that humans aren't amazing and special as we think we are, because we are just primates, and we aren't no longer the only primate that does these behaviours. Other primates and maybe even other animals have these cultures that were thought to be once defining of humans. So we can use nature to look into our own evolution, but we can also look into nature to try and predict our own future too. So on the island of Koram off East Thailand, there lives a troop of long-tailed macaques. So these are like little monkeys. And there's a troop of 80 of them living on this one small island. Now, these have also learned how to use tools, and they use different shapes of rocks. So large rocks or small rocks, rocks that have sharp edges, and they use these to crack open all the shellfish on the island. And if you look at other islands around Thailand, they still have the same long-tailed macaques, but they haven't yet learned this behaviour. So this population on Koram, they've developed their own culture of learning how to eat these shellfish with tool use. Now, they've been so successful, and it's made the population boom. As I said, there's now 80 individuals on this one small island. But their success is ultimately becoming to be their downfall. So one long-tailed macaque can eat up to 40 shellfish in a single day. Bit of maths here for you. Now remember, if there's 80 macaques and they eat 40 a day, that's 3,000 shellfish being eaten in one single day. So although they're very good at, learning how to get new resources and making their populations very successful, they're now exploiting their resources. And it's actually one of the first kind of opportunities that we've seen another animal that's not a human actively exploiting their own resources to a point where it can't sustain, it's not sustainable for a long period of time. So eventually what will happen is the monkeys will continue eating all the shellfish will run out, and it's already been seen that the shellfish are getting smaller and smaller because the adults are dying off and being eaten, and soon there'll be none at all. So it'll cause a localized extinction. And what happens when all the shellfish are gone? These long-tailed macaques, they'll have to find food elsewhere, and there won't be enough food resources to sustain that 80 individual population, which means that then, unfortunately, the macaques will start dying off too, because they can't be sustained. So by looking into this, we can kind of project it onto our own lives. So as we all know, humans are very, very successful. We have loads of industries and technologies, and our scientific advancements are coming on amazingly. But sometimes we have to take a step back and realise that kind of look at the speed we're going and think to ourselves, is this actually sustainable? Because although we're very good at imagining new technologies and stuff, we're quite bad as a species as a whole to think further than like immediate surroundings. So although we're making these great advances, can we sustain it? And therefore, can we sustain us too? So I think that's really nice that we can learn from nature things about our past, but also learn from nature to see how to continue to live into our future too. And that's it from me.
Thank you, Alice. Some thought-provoking examples there on predicting our own future. I think that's going to make me think twice when I eat shellfish. I'd like to now invite Belinda Rich to do her presentation on advanced materials for space habitats.
Yes, thank you, Nazira. And can I say thank you for inviting me to join this panel? I've already learned so much. So it's really exciting. I'm just going to share my screen here. Okay, so I'm going to talk about my work at the European Space Agency, where I work in a team called the Advanced Concepts team. And you may think that space, when you think of space, you think of things like rockets, satellites, not usually things associated with nature. But when I was invited to join this panel discussion, I realized that there are many things in design for space that are inspired by biology and by nature. So I'm going to give you just some examples of that in this presentation. maybe make you think that it's nature really does influence everything we do, not just things that are strictly biology related. To start with, when we, for example, if we want to build a habitat on the moon, NASA has already announced they would like to put astronauts back on the moon by 2024. In order to do that, we're going to need some sort of habitat. And here is an example of what that can look like. And in order to do that, we'll probably need to bring some things with us from Earth. Unfortunately, doing that can be very expensive because it costs a lot of money to propel rockets into the atmosphere, and you need to save on weight as much as possible. So one idea for how we can seriously reduce our weight costs if we would like to put a habitat on the moon, for example, would be to use a biological building material. An example of this could be mycelium, which is a material you can get from fungi. And that's really exciting because you only need really tiny seeds. You can bring them very easily with you in a rocket. It won't take up very much weight or very much space. And you can end up with structures that look something like this. This is a sculpture at the MoMA in New York. And this is a living building that is constantly growing. And these fungi structures have the ability to grow in space effectively, and they are very resilient. So this is what our astronauts could potentially be living in the future. But how about, rather than taking resources from space, how about using resources that are available to us on the moon? Unfortunately, the moon doesn't have any biological life. There's no organic material on the moon whatsoever. So to build things on the moon, the options we have are to use regolith, which is what we call the moon dust, the lunar dust. And we can make structures out of that using 3D printing, for example. And here in this picture, you can see an example of what that might look like. But we do, if we think about it and if we look closely, we do have options for a natural resource on the moon. And you may have spotted it. It's this guy right here. So we do have the potential for astronauts to provide us with a resource which might help us to build our habitat. In particular, that could be urea. And something that some members of my team have been working on is trying to think of how we can include urea from urine in our recipes to make a type of concrete, a type of cement called a geopolymer. And that's what this looks like. So you just take the moon dust, you can take astronaut urine and extract the urea, and you add some alkaline substances and you create a cement-like material. So that's really exciting. So just from the barren surface of the moon, where all you can see is moon dust, suddenly with just a little biological input, we have this cement-like material which we can use to 3D print with. So that's how using natural resources can really have an impact on our ability to perform some really huge projects like constructing on the moon, just with a little bit of input from the natural world. So that was one way that we take inspiration from nature in space. The other way we can take inspiration from nature is to replicate organisms and replicate really clever things we can see in nature, and use these techniques that nature has evolved for thousands of years. We can take these techniques that nature has and use them to improve our technologies. So I'll explain what I mean by that. I have two examples here. The first one is in satellites. So I'm sure everyone knows what a satellite is. We have many of them orbiting the Earth and going through the solar system. And as you can see from this is a Galileo satellite, which is one that we use for navigation, like on your mobile phone. That's what this is for. And as you can see, it has solar panels. And satellites gain their power from solar radiation. And you need, the more power you need, the bigger the solar panels you need. So that's where our power source comes from. But unfortunately, if you need more power on your satellite, bigger solar panels means extra weight, means a very expensive satellite to launch into space. So what if we could increase the efficiency of these solar panels so that each square centimeter of the panel can absorb more light and thus create more power? And so one way we have been thinking about how we can do this is to take inspiration from the bottom of the ocean, of all places. Because at the very bottom of the ocean, you have organisms like plankton and other microalgae, and they survive off sunlight. But unfortunately, you don't really get much sunlight at the bottom of the ocean. But nature is very clever, and these microorganisms have evolved to trap light very effectively. So this is a diatom, which is a structure that's very good at trapping light. So even with the very, very minuscule amount of sunlight that makes its way down to the bottom of the ocean, these organisms are able to synthesize the light and that they need to live. So, and they do this using these light trapping nanostructures on their surface. So one way we could improve our satellites in space is to look to the bottom of the ocean and maybe try and replicate these nanostructures to improve the efficiency of our spacefaring vehicles. And then the last example I have, Jack already mentioned the importance of honeybees, and honeybees are really clever, and they are in fact very, very good at the process of landing. They can land on any surface in any orientation. And they have perfected this using only visual information and a little bit of sensory information, just like your sixth sense of like knowing where you are in a space. Bees use that, and then they use their visual information to have a perfect landing every time. And that's really cool because when you land a aircraft, like an airplane, for example, you need a lot more information than that to accurately perfect your landing. You need to know your altitude and your velocity and all sorts, and that can mean a lot of sensors, and that can mean a lot of data and a lot of processing happening. So if we were to have an automated air vehicle in space, for example, this is a concept for a drone that could be used on Mars. These drones could be having a perfect landing every time using just visual data, and we can take inspiration from the honeybees and program our drones and our air vehicles to have the perfect landing every time using just visual information in the same way that honeybees do. So those are just two examples of how nature can provide some really, really useful inspiration for space, but there are many, many more examples. And yes, so I hope that has maybe got some people thinking about how nature does really impact a lot more of science and technology than you might expect. I will stop sharing my screen now.
Thank you, Belinda. Gosh, that was quite exciting. I thought I knew a lot about sustainable construction, but I think I've learned a few more examples here, which I shall take back to people I know working in that field. So thank you for that, and great images too. Our final panelist for today is Mark O'Shea, and Mark is a herpetologist. Welcome, Mark. You ready to present?
Yes, I am, Nazira. I'm going to be sharing my screen just to show a couple of images as well. I'm a herpetologist, which means I work on reptiles and amphibians. And what I thought I'd talk about was a really important aspect of how reptiles impact on humans. And that, of course, is snakebite. Now, you should be able to see there a slide that's showing the figures for the West African Ebola outbreak in 2013 to 2016, and it lasted 26 months, and there were just over 11,000 deaths, and that terrified the world. Now, it's rather hard to talk about deaths from Ebola or from snakebite in our current time when we are suffering such an enormous death rate from COVID. But COVID is the first really massive pandemic like this for 100 years. Ebola appears every so often, and snakebite is a daily issue. And if you look at the slide, you'll see that snakebite deaths every month, every year, are over 10,000. So in 1 month, it nearly equals the entire death rate from the 2013-2016 Ebola outbreak. And yet it doesn't attract international interest, funding. It doesn't raise concerns, and a lot of snakebite research has to ride along on the coattails of malaria research and other tropical diseases like that. And probably the reason for this is that snakebite is not a transmittable disease. Nobody can go and catch it and bring it back to your country. Whereas the fear with Ebola was obviously people returning from West Africa to the United States or to Europe might bring Ebola. And of course, we have that similar fear initially with COVID coming into the country. Snakebite is really the disease of the rural poor in the developing world. And this map shows you the situation. Everywhere shaded light red, pink, is where venomous snakes are found. And venomous snakes are my particular speciality and what I work on primarily. But I generally work on them from the snake's point of view. But because I've been working with them for a long time, I've ended up working on snakebite projects in places like Papua New Guinea, Myanmar, and Sri Lanka. Now, you can see the really red, bright red countries. Those are the ones, the top 12, with the highest snakebite deaths per capita. And they are all in West Africa, South Asia, or New Guinea. Up to 138 fatalities per year. 400,000 people permanently disabled, disfigured, lost hands, lost legs, unable to work. That's 20 times the number of people who are disfigured in a year by landmines, which is obviously something that people know about and care about because it was one of Princess Diana's projects. But there isn't the same sort of interest in people being disabled by snakebite, literally loss of limbs. These are often the breadwinners of the family and they can't work. Not only that, what about all the people who have been mentally scarred by their near-death experience or by the loss of somebody, a child in the family? And add to that the fact that healthcare isn't always free. And if your child has been bitten by a snake and you've got to pay for medical care, you will promise anything on earth to get your child treated. And families end up selling their goats, everything they've got, and they end up living in penury for the rest of their lives. So this is a massive issue, much larger than the 138,000 people who actually die of snakebite every year. And this should be more important. And fortunately, the World Health Organization have now included snakebite on their list of neglected tropical diseases and stated that they are going to try and bring down the death rate by 50% by 2030. So I thought I'd look at what snake venoms can do. There are snake venoms that have an effect on virtually every part of your body. The neurotoxins that cause paralysis and will actually lead to respiratory paralysis and death. Cytotoxins that will digest the tissue of your limbs. Venom in the eyes, if it's not washed out, will destroy your cornea so that you go blind. Hemotoxins that destroy your blood kidney failure due to direct attack on the kidneys by the venoms, or so much destroyed hemoglobin or myoglobin in your blood that goes to your kidneys that they end up getting blocked. You can see that there is almost no part of the body that cannot be affected by snakes, by venomous snakes. Now, venomous snakes are incredibly well adapted, and their venom is not primarily there as a defensive tactic. And you know, we think some people think that snakes are just out there to bite them, and this isn't true. Snakes primarily have venom for dealing with their prey, killing it, making it easier to swallow, starting the digestive process, etc. But it is a useful add-on that it can also be used for defense. The only snakes that have evolved a venom specifically for defense are, of course, the spitting cobras, which benefit from being able to defend themselves against a threat from 1 to 2 meters away. And it's actually believed that spitting evolved 3 times in spitting cobras, once in Asia, once in Africa, and once again in South Africa with the ringculls, which is a slightly different kind of cobra. And apart from the ringculls, the other 2 evolutions of spitting cobra venom and the tactic of sitting back and spraying venom into the face of a threat is believed in Asia and Africa to tally with when humans actually moved into the area. So they've got these large apes that, as Elise has said, are tool users and potentially carrying a club to ward off the snake, and the snake defends itself from a distance. So there's an interesting belief there that spitting cobras evolved to deal primarily with our ancestors. Now, if we look at the snakes that are actually primarily doing the serious damage in the countries that I've worked in on snake bite projects, there's always a big 4. And in Sri Lanka, the Russell's viper is the primary snake killing a lot of people. The antivenom that comes in from India does not address all the means that the venom of the Sri Lankan snake can cause, such as cerebral hemorrhage, which you don't come back from. And then, of course, Indian cobras, which are neurotoxic, common krites coming into buildings, biting people in the night. You may not wake up. It's a totally painless bite, and you may never wake again. And hump-nosed vipers, hump-nosed pit vipers, which are known to affect the kidneys. The Burmese big 4 include Russell's viper, but it's a different one, and its venom is very different to the one from South Asia. And even if you survive a bite from one of these snakes, it can cause your genitals to shrink and your hair to fall out. It is quite a nasty snake to be bitten by. And again, cobras, krites, and pit vipers. But in Papua New Guinea, you get a whole different group of snakes. The taipan being the primary culprit for killing a large number of people every year. And this was the species that we set out to try and deal with when we started to produce an antivenom for use in Papua New Guinea, because the existing antivenom coming in from Australia was so expensive that in Papua New Guinea, the health authority could only buy so much of it, and they would run out every year. And so what we wanted was an antivenom that was not as expensive, but was just as effective. And the original antivenom was like $1,500 to $2,000 a pack to treat a vial to treat one patient. The antivenom that was manufactured from venom that we took from Papuan taipans that we caught and kept in Port Moresby in a unit, probably the most secure place in the whole country because nobody wanted to break in there. And the venom that was milked was sent to Costa Rica to the University of San Jose, and they produced an antivenom which came back at about $150 to $200 a pack to save lives. So there was no reason for the Papua New Guinea medical authorities to run out of money. And some of the other snakes that are also killing people, Papuan blacks, rarely, but death adders and small-eyed snakes. And one of the things I've noticed is that nature has a kind of payback. Humans now, well, they have for 150 years, 200 years, been building plantations, rubber plantations in Malaysia, coffee plantations in the highlands of New Guinea. Now all the oil palm that's threatening Elise's orangutans in Borneo and in New Guinea, also a lot of oil palm. All of these monocultures, for some interesting reason, they become hotbeds for venomous snakes. They have a much lower diversity of snakes living there, but the species that are found there seem to be found in much denser numbers than they would be in the pristine habitat nearby. And because of all the rodents that get attracted into these habitats, you end up with a very high number of venomous snakes. And we know oil palm plantations in New Guinea with enormous numbers of taipan. We know of oil plantations in Borneo with very high populations of spitting cobras, and tea plantations with large numbers of arboreal pit vipers that bite the tea pickers. And so almost like nature's payback. And if we continue to put monocultures around the world, we will increase these huge populations of venomous snakes, and we will need a lot more anti-venom.
Thank you, Mark. And I'm sure some of our panelists will have further contributions to make in terms of that link of habitat and the work we do in terms of growing food and the demand, increasing demand for resources, and how that brings with it these different challenges and these changes. So thank you for that, Mark. At this point now, we've had all four panelists giving your presentations, which were, very different, but each one demonstrating the impact that not only humans, but the other organisms we live beside have on the environment. So what I would like to do now is to thank you very much for your presentations, and very, very thought-provoking, and some quite humorous stories too. Thank you, Belinda, for sharing some of those lovely images, and I think some materials that I wouldn't have thought about. Jack, for the environmental context and the connectivity, and LS for talking about the cultures within the primates. And I loved your story about the blowing raspberries before going to bedtime, and might adopt that myself. And Mark, I know there's further discussions that you want to have with the panelists around the natural environment and humans in terms of the venomous snakes, and how we are able to bring that into our medical laboratories as well to treat diseases. So just an opening question from me to the panel. What are some of the ways people in your field are making a difference to the world? So if you could, pick up one or 2 points that you think really highlight that contribution in terms of making the difference. And this time we'll start with Mark. I think, I think the bits around the venomous snakes was really crucial, and that stuck in my mind. So just bring you in, Mark.
Well, the production of antivenom is an extremely important issue, and people might not be aware that we are actually going into an antivenom crisis. Drug companies have been pulling out of the manufacture of antivenom, and the problem is extremely serious in Africa, where there is the main producers there, which were German and French companies, no longer produce antivenom for any of the snakes of Africa. Antivenom is produced in South Africa, but it doesn't cover everything. And one of the things that I think is surprising and something that I think is very, I say, altruistic, is the fact that the Costa Ricans at the Institute of Clodimira Picado are not only producing antivenom for Costa Rica, not only producing antivenom for Central America, not only also when it's needed for South America, but they have moved into producing it for Africa, South Asia, and Papua New Guinea. And this is a university institute that have gone beyond the problem. They've dealt with their problem, and they're now trying to assist with other problems. And this isn't a big multinational drug company. This is a university institute. And I could not fly the flags high enough for Institute to Clodimira Picado because of the actions that they are taking.
Thank you, Mark. And Belinda, you've given us some examples already, but would you like to pick up some other new ones that we're not aware of in your field?
Yeah, so a lot of the examples I gave earlier were very specifically focused on the future of space technology. But what people might not often think about is that space affects our daily lives all the time. And a huge part of what the European Space Agency does is Earth observation. And so this is really important for forecasting the weather, for example. That's probably the one most people would think of. But also monitoring issues that are really important to the natural world. For example, deforestation. We are able to monitor the change over time in greenery that our satellites picks up. Our Earth observation satellites pick up, and other things like the ice melting at the Antarctic and the Arctic, and also Earth observation satellites from ESA were really useful during the forest fires that happened last year and also earlier this year, I believe. And it's really important for monitoring how these huge events, which unfortunately have a huge toll on the environment and on the Earth, but we are able to monitor these things from space to see how they're spreading and make better decisions about how to stop it more quickly.
Thank you, Belinda. Alice?
So when we talk about primatology, obviously we always just assume primate behaviour, and sometimes I think it can be a bit difficult to kind of relate how does behaviour impact the world, like why does it matter if we know how a certain animal acts? But actually it's knowing this behaviour that we can then put certain things in place to conserve the animals, and by learning the behaviour of these animals we can learn more about not just conserving them but conserving the ecosystem as a whole. So obviously, like in the primate world, there's so many fantastic researchers and scientists are out here all working together. There's so many societies, such as like the International Primate Society and the Primate Society of Great Britain. But I just want to talk about a few where I worked primarily in Madagascar, because obviously there's a lemur over there, the primate. It's actually the only country in the world that has lemurs. And there's so many good people and good scientists working with these lemurs. We have, for example, Dr. Christoph Switcher, who works in Bristol Zoo. We have Dr. Giuseppe Donati in Oxford. And there's so many more. These are just like two off the top of my head, but there's so many more that are working to record all these behaviours. I've actually found out that by studying behaviours of these lemurs, we found out that they're actually so important for their ecosystems. So they're what we call a keystone species and an indicator species. So obviously a keystone species is an animal that is so important to that ecosystem that without it, the whole ecosystem would fail basically. And an indicator species is that if you see this animal in an area or lots of these animals in the area, the quantity of these animals kind of suggests the health and of the overall ecosystem. So what we have found out is that these lemurs are so important because they're actually seed dispersers. So like think of it as a big honeybee. So they're like pollinators. They get the seeds from the trees and they disperse them around the forest and encourage new growth. And actually, without these lemurs, the forest wouldn't be able to regenerate. And that, like I said, they're so crucial for the environment that if they weren't there, and if we do lose them, which they are one of the most endangered mammals and probably animals on the whole planet at the moment, if we did lose them, then pretty much we're looking at losing whole forests and whole ecosystems. So I think that's just really nice to say how experts in primatology are actually helping not just primates, but the entire ecosystems of areas too.
Thank you, Alice. Now, Jack, you've got a wide field to choose from, unlike the other three, which was very specific. So I'll leave that very open for you to choose and come up with what you think.
Sure, thank you. Well, I guess one of the first things I would remind people of is that environmentalism, as we know it, it's really a fairly new discipline. I mean, over the past 50 years, it's really developed. And one of the key founding principles that it's based on for Greenpeace and other organizations is bearing witness. And this is linked to what Belinda was saying there. If we don't know and we can't record the things that are happening, then we can't act upon them. And I think bearing witness has become one of the hugely important factors of environmentalism. You have to be there in the first place. You have to expose these things to the world. And not just to the experts. I think the experts are the ones who can then deliver afterwards. But often what we see is without a public outcry and a public response to very important issues, the experts unfortunately don't always get listened to, at least in the political sphere, as we're seeing more and more across the world. No names mentioned, obviously. But I think another very, very important thing is the legitimacy that's been gained over those years for the environmental movement. We're seeing an increasing number of court cases at the moment where governments and corporations are being held responsible for emissions that go counter either to national constitutions or to the Paris Accord, for example. Just last week in Norway, we met the government in Supreme Court to combat their reckless drilling in the Arctic, for example. So that's obviously extremely expert driven. And the final thing that I'll just touch on, though there are myriads more, is the shift in focus of responsibility. And this is something that is massively, massively important as we try to elicit large scale environmental change. Is many governments and corporations have made the active decision over the years to put all of the focus on the user and the consumer. You need to recycle, you need to pick up your litter, etc., and the problem will be solved. Maybe if we'd started off like that, the problem would be solved. But it shifts the onus onto individuals and gives these quite destructive corporations carte blanche to continue exploitative policies. So I think the balance of power is shifting, and people are becoming more and more aware that whilst it's great to take those personal actions, the true power to elicit that great change must come from the corporations who are creating the damage in the first place. And that's why we as individuals can use our impact and input to put pressure on those corporations instead of feeling guilty for not changing the world ourselves.
Thank you, Jack. You actually started and have answered my final question to the panel. And so my question is, from what we have learned from nature, how can we now make a substantial difference? And I think you've answered that. Do you want to add any more before I move to the next panelist?
Yeah, I just think going back to the previous presentation as well, is just read the signs. Nature is communicating with us at all times. And if we read the signs and we take individual actions, but put pressure where pressure is due, then we can make real change. And that's about it.
Thank you, Jack. And bring in Belinda at this point.
Yes, so I thank you, Jack, for your really thought-provoking comments. Just from the perspective of the space industry, we've seen that space is very far removed from nature, about as far removed from planet Earth as you can get. But we can still see that nature has an immense amount of value, and that we can still learn so much from the natural world, and taking inspiration from it. So I think the key takeaway there is that it is very precious, and even though we are moving into a technological age where we are boldly going where none have gone before, it's still very key to value what we have on planet Earth, the natural world, which is so clever in so many ways and so valuable, and it's very important to preserve that.
Thank you, Belinda. LS, any final thoughts from you on this?
Yeah, it just kind of mirrors what Jack says, really, about like people taking responsibility, and importantly, large corporations taking responsibility. I think now more than ever, we're as a whole, we're so more aware of what our actions have on the Earth and what impacts even individual choices can have on the planet. And even more so now, like with TV, like David Attenborough's last two films that he did, they were really thought-provoking. And it seems like the shift has gone from celebrating wildlife to kind of protecting wildlife, which is what I really like, because it's really hard, because we're quite removed from it in big cities and urban areas. We are quite removed from seeing the actions, the consequences that our actions can have the potential to do. And I think just take an hour out your day, just go for a walk, just even look out your window and just look at all the nature that you can see around your area. You'll find so much nature around your area, so many animals. And then just think about how many more animals there are that you can't see. Look at the products that you use. For example, I've got some chocolate milk here. Look at the chocolate milk and think, where did that soybean come from? What animals are being potentially harmed by that? So once we start kind of thinking, I like to say thinking more eco than thinking more ego. Once we start thinking of everything in turn, like we are part of the world, we're not humans that are superior, we are part of the world, and there's other animals like our primates, our close relatives, that they are our distant cousins. Once we start respecting that and wanting to help them, I think the world will be such a much better place in general.
Thank you, LS. And Mark, some final thoughts from you.
Yes. I mean, I've spent my time on this panel talking about the terrible damage that venomous snakes can do, and I feel that I should also speak up for venomous snakes as a conservationist, because they are part of the ecological jigsaw, and they play their part. They are climax predators. They feed on a lot of rats and mice, which, if there aren't controls on rats and mice, the populations get out of hand. And snakes are one of the best natural mouse traps, rat traps out there. And if you've looked at a paddy field in Sri Lanka, you can see the rat damage that's done to paddy fields from the air. It almost looks like crop circles. It can be that considerable, and that the snakes are preying on those. And quite apart from the fact that they're an important part of the ecological jigsaw, and who wants a jigsaw with a piece missing, they also, their venoms being so complicated, so diverse, there are medical uses for a lot of the venoms. There was a drug produced using the venom of Malayan pit viper, which was used in cardiac surgery to prevent the buildup of clots afterwards, which you don't want to clot if you've just had heart surgery. And so this venom was used in this particular drug. Now, obviously now, a lot of these components can be synthesized, and you might not need the actual snake venom, but that's where the research is. And snake venom has been examined and investigated for use in things as diverse as MS and cancer. So, you know, there's a lot of potential out there if the research and development is done on snake venoms alone.
Thank you. Thank you, Mark, and thank you to all four panelists. it's been a real pleasure having you join us for this panel session today. And the topics that you have discussed have given us really some thoughts that have given us some thought-provoking, have given us some, now I can't even speak. So thank you to all the panelists. Your talks today have really been very thought-provoking, and you've given us examples where nature has sparked some really significant and important developments, but also have gone on to also inspire scientists and artists and environmentalists. So some really good examples there, also looking into the future. And I'd like to end with, I think, I forget, one of the panelists have said about predicting the future, nature helping us predict the future and advance from where we are. So thank you very much for your time. And thank you for your contribution to this workshop and this event. Bye.
Thank you.
Thank you.
Thanks very much.
Well, just to echo what Professor Karodi has said there at the end, amazingly thought-provoking stuff from all of our panelists. So I'd like to say a massive thank you for everybody who was involved in that event. I was absolutely blown away by some of those discussions that were there when I was watching. And again, thank you to the panelists who have been answering the questions for our participants in the chat. To be able to have interaction from you actually live for the people watching has been absolutely fantastic. Now, this brings us to the end of our journey today through science, technology, engineering and maths on our Saturday STEM Spectacular. I'd just like to say a massive, wholehearted thank you to everybody who's watched all the way through our event today. And a massive thank you again to everybody who's contributed their time and their effort to make videos, to make this actual event what it was today. I need to thank, of course, the Association for Science Education for collaborating with us to actually make this event possible. And above all, I'd like to say a massive thank you to the External Engagement Department at the University of Wolverhampton for making all of this transmission possible today. But there is one person really here today, and she's sitting sort of over there in the office. She hasn't got a camera on at the moment, but that is Heather Angel, one of our fantastic members of the STEM response team, because she has put together this whole event, done all the video editing, made all the things that you've seen today, and joined it all together to make this fantastic event today. So I'd like everybody out there to give her a fantastic round of applause, because without her, this literally would never have happened. So I'd like to say goodbye from the STEM response team and goodbye from the University of Wolverhampton. Have a great day. Goodbye.